Let's take a ride. More to come in this marathon.
The universe is full of both verified and hypothesized objects that do not fit neatly into the humdrum world of standard classes of planets, moons, galaxies, and well-understood phenomena. So here are 10 bizarre deep space astronomical objects that have either been discovered or may well exist out there somewhere amongst the stars. Number 10. Moons. One of the most common questions I get is, can a moon have its own moon? And the answer is yes, or so it's thought. While no example of this kind of object has ever been discovered, it's one of those instances in astronomy that seems likely to eventually happen. It's the concept of a subsatellite, or moon, where a moon of a planet has a moon of its own. While in most cases this isn't likely to occur in a planetary system, there are situations where it can. And indeed, we ourselves have created artificial moons in orbit of our own moon, though doing so is tricky. There are, however, natural candidates for this. Saturn's moon Iapetus has a very pronounced, unusual ridge extending around it that may have been caused by a past moon. But even stranger is the case of Saturn's moon Rhea. Last year, what appears to be a ring system was discovered around this moon, creating the odd situation of a ringed moon orbiting a ringed planet. It was determined that if it had a ring system, the tiny moon could have a stable moon in principle. A search of the data from the Cassini mission has failed to find such a moon, but it does tick a box in favor of moons existing in the universe. Number 9. Rogue planets. At first glance, interstellar space may seem very empty other than dust and the occasional atom of hydrogen, but in reality, interstellar space also hosts an entire class of planet that sits alone from planets confined in star systems. They are rogue planets. Rogue planets typically start as members of star systems, but instabilities within those systems leads to their ejection. Indeed, it's thought by some scientists that early in the solar system's history, a Neptune-sized planet that formed here was ejected through a close encounter with Jupiter. Where that planet is now is anyone's guess. But having been ejected an estimated 4 billion years ago, it's likely very, very far away. One candidate for a free-floating rogue planet is an object known as SIMP J013656.5 plus 093347. Once thought to be a brown dwarf, the size of this planet has been constrained down to 12.7 Jupiter masses, making it seem more like a massive planet than a brown dwarf, though the line is blurred. The object is particularly interesting because variations in its light curve have been interpreted as variations in cloud patterns in its atmosphere, and indeed evidence for very powerful auroras has also been found, suggesting that the planet has a very strong magnetic field. Apart from giant worlds, there should be a population of smaller rogue planets as well, including planets that might have otherwise been similar to Earth. Interestingly, the concept of a rogue planet wandering the darkness of interstellar space doesn't seem conducive to life ever arising in such a place. But with geothermal heating, such a planet could have liquid water. Who knows where life might get a foothold, though it might seem rather sad if a rogue planet is ever discovered that had evidence of life, but that life went extinct long ago when the planet froze over in the depths of space. Number 8. The antimatter fountain. The matter-antimatter reaction is the ultimate inefficiency. If you have exactly 1 gram of matter and 1 gram of antimatter and put them together, they will violently annihilate each other in a 100% conversion of mass into energy. But there is a rabbit hole here. There is no clear reason why the Big Bang wouldn't have produced equal amounts of matter and antimatter. For some reason, not yet understood, it seems that slightly more matter was created than antimatter, allowing for the universe's matter to exist today as we see it. But antimatter can still be created, even in nature. At the center of the galaxy lies an antimatter fountain that spews massive amounts of positrons out, which then go on to annihilate on contact with normal matter. What's actually at the heart of the fountain producing this material is unknown, but hypotheses range from them being somehow created by a black hole, or even that they are somehow being created by some reaction involving dark matter, though no one knows how that would even work. Number 7. The double quasar. This entry is a kind of 1-2 punch in strangeness, not only because of the nature of what it is, but also a strange occurrence associated with it that was caught entirely by pure chance. In 1979, the object QSO 0957 plus 561 was discovered. Initially, it appeared to be 2 quasars located very close to each other, something that seemed unlikely. As study of the object progressed, it was realized that the two quasars were so similar that they would essentially have to be twins, making the whole thing even more unlikely. Later, instead of being two quasars, it was found that they were actually two images of the same quasar that were being gravitationally lensed by a galaxy in the foreground. This was one of the first gravitationally lensed objects ever found, and confirms Einstein's view of space-time being warped and capable of lensing objects. And there's an interesting effect with this case. Any change in the quasar is seen in one image, but because the other image represents a slightly different path, the same change is not seen in the other image for over a year later. This quasar also happens to be extremely distant at 7.8 billion light-years, and the galaxy that is in front of it, just over half that. This led to a strange incident in 1996. Astronomers caught an odd dip in the light of the quasar. Unfortunately, it can't ever be confirmed, but one idea that's on the table for this dip is that it was caused by the transit of a 3 Earth-mass exoplanet in front of the quasar. This would place that exoplanet within the galaxy that's lensing the quasar, and would be by far the most distant exoplanet ever detected, at a whopping 4 billion light-years. Number 6. Omega Centauri. The Milky Way is full of spectacular star clusters. These are full-fledged members of our galaxy having formed here, but one stands out, Omega Centauri, and it's not just any star cluster. It's very brightly visible from Earth, even at a distance of nearly 16,000 light-years, and it basically breaks most of the rules that define globular clusters in the Milky Way. For example, a typical star cluster of the Milky Way has hundreds of thousands of stars, such as M80, which is visible in small telescopes. By contrast, Omega Centauri has millions of stars. Globular clusters in the Milky Way tend to be a bit homogeneous as far as the types and ages of the stars within them. Omega Centauri is not like this at all, and contains a varied profile of stars all born at different times, evidenced by their types and metallicities. And the whole thing is spinning, which normal star clusters tend not to do. All of this points to an unusual origin for Omega Centauri. Rather than being a member of the Milky Way, it may not be from here at all, and could represent the nucleus of an entire other galaxy that the Milky Way absorbed and cannibalized at some point, until all that was left was the core. This would mean that scattered across the Milky Way are stars and possibly planets from another galaxy entirely, and this process of galaxy mergers has not stopped. Indeed, we are currently careening towards the Great Andromeda Galaxy for a merger in about 4.5 billion years. Number 5. Hoag's Object. When this object was first discovered, it wasn't immediately clear just what it was. One idea is that it was something similar to the double quasar, and that it was a quasar behind a foreground elliptical galaxy that was being gravitationally lensed around it. This did not turn out to be the case, however, and as it turned out, the object is actually a cohesive galaxy, yet it's structured very differently from normal galaxies. Instead of a normal spiral galaxy structure, this object has a core of older, yellower stars, then a large gap, and then a blue outer ring of generally younger stars. There aren't any dead ringer answers on just how this came to be, but on the table is a very specific encounter with another small galaxy, where it barreled through rapidly, creating the effect. But this would have had to have happened relatively recently, and no small galaxy seems to be in the vicinity. Another is that it is the result of some type of instability that can happen in barred galaxies. Yet Hoag's object doesn't appear to have ever been a barred galaxy. No option fully explains just how Hoag's object came to be this way, and it's unique. While there are other ring-type galaxies, they are very rare, and none are quite like Hoag's object. And to add another enigmatic twist to this story, is that rare as they are, there is a second ringed galaxy at a completely different distance and totally unrelated to Hoag's object that just happens to be lined up just so as to appear within the gap of Hoag's object. The chances of two very rare galaxies appearing like that are, well, astronomical. Number 4. SN 2006 GY. It's hard to envision anything more cataclysmic than a supernova. There are two main types. Type 1, where a white dwarf gains material from a companion star until the accruing mass causes the white dwarf to begin fusing carbon and the star explodes. Type 2 is the more familiar stellar collapse of an old star, ending its life by imploding and exploding. But there appears to be a rarer third type, and one was witnessed in 2006. This was SN 2006 GY and exploded with a violence estimated to be as much as 100 times the power of a normal supernova, in essence, a hypernova. Stars that can do this must be enormous, the largest stars in the universe, and the rarest. And they don't live long. They tend to only live for a few tens of millions of years before exploding. While it's not entirely clear how these massive explosions occur, one idea is that stars this massive produce gamma rays, and that in turn can create matter-antimatter pairs. This creates a matter-antimatter reaction as they annihilate each other, which then goes out of control inside the star, causing it to collapse and explode. This type of supernova is odd in another way. In a normal Type 2 supernova, a neutron star is left behind, but in the case of these giant supernovas, the star is entirely blown up. And another of these is coming, and it will be much closer. SN 2006 GY was in another galaxy entirely, but the Milky Way star Eta Carina is just this type of star and could explode at any time. When it does, it won't pose a threat to Earth, but it will be a spectacular sight and will probably be visible from Earth even in daylight for a time. Number 3. Thorn-Zeitgau objects. These strange objects are still only hypothesized to exist, though there are candidates for them, and they likely do exist, though are probably very rare and probably limited to very dense areas of stars, such as globular clusters, and in very special circumstances in binary star systems. So rare that there could be as few as 20 of these objects in the Milky Way at any given time. A Thorn-Zeitgau object forms when a neutron star collides with a giant star and essentially becomes engulfed within it. If the combined two are of a high enough mass, the whole thing will collapse into a black hole, and probably creating yet another type of supernova. If not, the strange state of affairs will eventually result in a single, more massive neutron star. While no confirmed Thorn-Zeitgau object has ever been discovered, there are several candidates. One particularly interesting system is where an F-type star is being orbited by an unseen object, likely a black hole. It's thought that this system, GRO J1655-40, might have went through a stage as a Thorn-Zeitgau object. Number 2. Stephan's Quintet. This strange case is an instance where one solved mystery leads to another. That is not uncommon in science, to say the least, but in this case, solving the first mystery ended up reopening the very same question. The objects in question are a group of galaxies known as Stephan's Quintet, and the mystery involves redshift. Redshift is a major way of determining distance and motion in the universe, in this case, the distance to these galaxies. At first glance, the galaxies in the quintet appeared intertwined, as if they were all physically connected with each other. But there was a problem. The redshift of one of the galaxies, the one at the lower left, indicated that it was only about 300 million light-years away, whereas the rest were 10 times more distant. So, how could they be interacting? Were scientists completely wrong about redshift? This led to questions about whether redshift can be trusted. This was an uncomfortable prospect, because if it had been wrong, then we'd be wrong about distances in the universe, and even the size of the observable universe. It wasn't until the year 2000 that the mystery was finally solved using the Hubble Space Telescope. They imaged the galaxies and found that the oddball galaxy's individual stars could be resolved, and the other galaxies could not be. In short, it was an optical illusion, and the oddball galaxy had to be 10 times closer, and the reliability of redshift was safe, or was it? Not long after, the mystery arose again in the same group of galaxies. Another of the galaxies had an odd star-like feature near its nucleus. Spectroscopy showed that the object is in fact a quasar with an enormous amount of redshift, suggesting that it's billions of light-years further away than the galaxy is. Yet it appears to be in front of the galaxy and interacting with it. In the end, Stephan's Quintet opened up more questions than it answered. Is there something wrong with redshift? Is there just a chance hole in the galaxy that allows the quasar to be visible and the interaction is just an illusion? Is there something wrong with our interpretation of quasars? The questions are open. Number 1. Diamond planets. Carbon is a very common element in the universe, and indeed forms the basis for the chemistry of life itself. In protoplanetary disks, it should be possible that ones rich in carbon but poor in oxygen might exist. These would in turn form a very different kind of planet to anything in our solar system, a carbon planet. While there is at least one candidate for this type of planet, 55 Cancri, none have been confirmed. That particular planet seems to have a surface made up of graphite and diamond, but it's also very hot. Carbon planets would be very different planets indeed. If a carbon planet that has sufficient pressure internally, it might maintain a thick layer of diamond from which material might be transported to the surface through volcanism, creating diamond volcanoes, such as what might be happening at 55 Cancri. Cooler versions of these planets might sport liquid hydrocarbons on their surfaces, but what they probably wouldn't have is water. That doesn't preclude life on a world like this any more than it does on Titan, but that life would probably be forever microbial if it could happen at all. But within this is an even stranger object that probably can't be called a planet, though it would look like one. Orbiting the millisecond pulsar PSR J1719-1438 is a planet-like object that appears to be almost entirely made of solid diamond. And it's known to be very small, yet has a mass similar to Jupiter, but this object didn't start out as a planet at all, but rather a star. The spherical chunk of diamond is the remnant of an apparently evaporated white dwarf. In short, it's a diamond star cinder. The local neighborhood of objects near the Sun is rather extensive, consisting of small stars, larger ones, brown dwarfs, interstellar objects, and so on. All are interesting in their own right, but some star systems nearby the Sun stand out. So here's a sampling of 10 of the nearest systems and what they are like. Number 10. Ross 128. Located at about 11 light-years out is the red dwarf star Ross 128. This is a very low-mass star, at only about 15% of the mass of the Sun, and if you were near it, it would look much, much dimmer. But it's also a very old star, determined by low amounts of any elements other than hydrogen and helium, placing it nearly 10 billion years old, twice the age of the Sun. Most interestingly is that this star has been found to have a planet. Known as Ross 128b, it's thought to be just slightly larger than Earth. This planet orbits very close to the star and is most likely tidally locked, always presenting the same face to the red dwarf, and seems to be on the inner edge of the habitability zone of Ross 128. The question of whether it might indeed have life is a complicated one. Red dwarfs, when they are young, tend to be violent and flare a lot, disfavoring a world like this from being habitable. Yet Ross 128, while it does flare, is on the quieter side of that due to age. If an atmosphere was able to survive on Ross 128b, then it's conceivable that the conditions might be right for liquid water and life now, or not. Oddly, Ross 128 was also the source for one of SETI's biggest false alarms. In 2017, a radio signal was picked up by the Arecibo Radio Observatory that appeared unnatural and seemingly coming from the star system. The signal wasn't picked up again by other telescopes, but what they did pick up was a lot of human-made interference. Given Ross 128's position in the sky, it turns out that in the same area there are lots of geosynchronous satellites, and it seems most likely that the signal was a satellite downlink, and not likely to have actually originated from the star. Another interesting thing is that Ross 128 is currently moving towards us, and in about 70,000 years it will pass just over 6 light-years from the Sun. One can imagine that with 70,000 years of technological development, this star may one day be seen very close up by human eyes. Number 9. Epsilon Eridani. This star has the distinction of being visible to the unaided eye from most of the surface of the Earth. Located in the constellation Eridanus, this star is about 10.5 light-years distant. This star is considerably younger than the Sun, estimated at only about 1 billion years old. It could be called sun-like, but not very much so, being a Type K orange dwarf. Given its youth, this makes for a somewhat more active star with strong solar wind. Epsilon Eridani seems to have a giant exoplanet orbiting it, though this is not fully confirmed, but at this point seems probable. We also know that this system hosts 2 asteroid belts. While not a certainty, these belts may be maintained by a second planet. We also know that this system has a really extensive debris disk, not unlike our own Kuiper belt, which is probably home to planetesimals left over from when Epsilon Eridani formed. In the past, this star has been subject to several science fiction stories and has been periodically checked by SETI just in case, but it's unlikely that this star has had time to develop any kind of intelligent species. Though it may have life itself, it's perhaps in a simple form at this stage, as orange dwarfs seem to be good candidates for habitable planets, and they last significantly longer than stars like our Sun do, so there will be more time for evolution to do its magic, should there be a suitable world in that system. That's if humans don't colonize any planets that might be there as we spread out into space before intelligence has had a chance to arise on its own there. Number 8. Luyten 726-8. Despite being one of the closest stars to the Sun at 8.7 light years, the system was not discovered until 1948. The system is made up of a pair of very similar red dwarf stars that orbit each other about once every 26 years. The system actually used to be closer to the Sun at just over 7.2 light years, but has moved away since. Both are flare stars, and in fact one of them serves as the archetype for that class of star, the UV SETI type variable star, but one member of the system is rather extreme in its changes in brightness. In 1952, the star was seen to increase in brightness so rapidly that it increased by 75 times in only 20 seconds. While this double star system doesn't seem likely to have planets, it may actually threaten another entry on this list that might, Epsilon Eridani. In just over 30,000 years, this system will pass close enough to Epsilon Eridani to disturb its Oort cloud equivalent. This could send a hail of comets into the Epsilon Eridani system, conceivably setting up an extinction event on any planet that might harbor life there. Number 7. Sirius. Sirius is especially noteworthy in that it's the brightest star in the night sky. Sirius is close at only about 8.6 light years and comprises a binary star system. Interestingly, this system is only going to appear to get brighter for the next 210,000 years as it moves closer to the solar system. After that, it will gradually dim until it is no longer the brightest star in the night sky. The system is young, only about 200 to 300 million years old, and consists of the principal star in the system, Sirius A, a bright bluish star about twice the size of the Sun, and Sirius B, a white dwarf which just over 100 million years ago swelled into a red giant, and then settled down to become a white dwarf. This is also in store for Sirius A in less than 1 billion years. This short lifespan makes this system unsuitable for life as we know it, at least, but there is one other aspect of the Sirius system that should be explained. Over the years, television programs and popular books have made the claim that the Dogon people of West Africa were impossibly aware of the companion star to Sirius A before such a thing could be detected, as it's nothing close to being visible to the naked eye. This was reported about a century ago by an anthropologist who was apparently unaware that previous visiting scientists looking to observe a solar eclipse might have told stories about the telescopic discovery of Sirius B, which was confirmed and observed in 1862, and that the Dogon might have been telling him about that. Then everything sort of went off a cliff in the 1970s, where people were claiming that the Dogon had contact with aliens from the Sirius system, and many books were sold. Trouble is, the Dogon are still around, and no one at the time seemed to think to go out and ask them for a clarification. In the early 1990s, further anthropological work found that none of this was quite the case. They found that the Dogon did revere the star to some degree, not surprising since many different peoples have, and it's useful in agriculture, calendars, navigation, etc. But they seem to no longer have a coherent narrative surrounding the star as had been reported in the 70s and 80s pop culture. To some within their group, its appearance announced the beginning of a festival, but others said it was actually Venus, and sometimes the two were interchangeable. What they did seem to agree on is that they first learned information about the star from Western anthropologists rather than an alien. They even remembered specific names. Number 6. Teegarden Star. Teegarden Star lies about 12 light years from our solar system and is another red dwarf. Not surprising since they are by far the most common types of star in the universe. This star was unknown until relatively recently. It was only discovered in 2003. This in itself opens up a question. If dim red dwarfs like Teegarden Star can remain undiscovered until modern times, then do other dim red dwarfs nearby remain undiscovered? That seems likely, and in the coming decades, more may come to light, and they may be very interesting indeed. Teegarden Star, however, is barely a star at all, just slightly more massive than a brown dwarf. But the star system seems to host at least 2 Earth-sized exoplanets, both of which are marginally within the habitable zone of the star. It's hard to say whether these planets have maintained atmospheres and could have liquid water. That's still debated. The possibility of life is an even greater question. But this star system does illustrate that it's conceivable that the most likely star systems nearby our solar system that might harbor life may yet remain undiscovered. Number 5. Lalande 21185. Another red dwarf, Lalande 2011-85, sits at about 8.3 light-years away, though this is shrinking, and in just under 120,000 years, this star will pass only 4.6 light-years from the Sun. The star has been known for a while. The Lalande catalog dates from the early years of the 19th century. This star, while oddly classed as a variable star, is actually on the calmer end of things for a red dwarf. Most noteworthy about this star, however, are claims of a planet. This was actually one of the earliest claims for the detection of an exoplanet, going back to 1951, a time when it would be decades before we even confirmed the existence of planets outside the solar system, though in fairness, they were strongly suspected to be out there. But in 1974, the claims for this system were refuted, and it seemed that the system had no planets that were detectable at the time. Oddly, the same researcher that refuted the earlier claims would go on to announce the discovery of planets in this system in 1996. This world has also been called into doubt over the years, at least until the Keck Observatory seemed to have found indications of an unpredicted close-in planet in this system. Further study has shown that this planet is probably about 3 Earth masses, and whether it's actually there would be in an orbit that would place it too close to the star to be habitable. But given the changing nature of the question of whether the star system has a planet or multiple planets, more could very well be discovered. Number 4. Wolf 359. This star is a case where science fiction meets reality. For science fiction fans, this star was most famously the setting for the Battle of Wolf 359 between the Federation and the Borg in Star Trek The Next Generation, where things got just a little too close to Earth for comfort. But the star actually does really exist, and while little was said about it in Star Trek, it's actually quite an interesting neighbor to the Sun. Located just 8 light-years away in the constellation Leo, Wolf 359 is a very dim red dwarf, even after being one of the closest star systems to us. The reason for this is that it's very faint and low mass, about 9% that of the Sun, and not that much larger than Jupiter, and is actually cool enough to allow for chemical compounds to form within it without being destroyed. But the star is also magnetically very active, more than the Sun is, and as a result is another flare star that undergoes sudden increases in luminosity, including X-rays. This particular star was first of interest to German astronomer Max Wolf, who was looking at the proper motions of stars, or how fast they appear to move through space. A high proper motion typically indicates that a star is close, though not always. Wolf's work was to catalog stars with high proper motions, and to this day the catalog remains in use, hence the term Wolf 359. It's number 359 in the catalog. But there's one aspect of Wolf 359 that makes it really interesting to a far future humanity. This star is fully convective, which means that it circulates its hydrogen throughout the star, including refueling the core, and it seems to be relatively young. This means that this star is going to last a ridiculously long period of time, to the tune of 8 trillion years. In comparison, the Sun will go red giant in about 4.5 billion years, and that's where exoplanets come in. In 2019, it was found that this system may have at least 2 planets within it. In the far future, perhaps some planet around the star might make for a second home for humanity, one that will last far longer than our system of origin in its current state. Number 3. Tau Ceti. This star system differs a bit from many of the other entries on this list because it isn't just some tiny dim red dwarf, but a very sun-like star. Tau Ceti is a little smaller than the Sun, about 78% its mass, but it's very similar in many other ways, and shares the same Type G classification as the Sun. If you were nearby on a planet in this system, this star would look a lot like the Sun. Currently located 12 light-years away, Tau Ceti is notable for being really calm, actually more so than the Sun. And there is certainly material in this star system. It's a very dusty place with as much as 10 times what we have in this star system. More on that in a minute. And it's a problem for an otherwise important star to SETI searches. In addition to being similar to the Sun, Tau Ceti is believed to be older, though this is debated, but possibly as old as 10 billion years or more, but probably closer to 5.8 billion years, or maybe a little younger, which, either way, would in principle give evolution on any planet in the system within the habitable zone plenty of time to form life and a civilization based on what happened here on Earth. The habitable zone of this star would be closer in than it is in our own solar system, but not that close in. It would land about the orbit of Venus if Tau Ceti were our Sun. All of the similarities between this star system and our own have led to past SETI searches for signals to no avail, and while Tau Ceti does appear to have planets, at least 5 to date, 2 apparently within the habitable zone, we hear nothing. But then comes the debris, and that might provide an answer. This system appears loaded with comets and asteroids, and that's a problem for life, at least of any complexity. While simple life on these planets may exist, and maybe even more complex forms of life occasionally, it seems likely that things would simply get reset by impacts at a rate far higher than they happened here. On the other hand, the bulk of this debris seems to be outside of the habitable zone, which may change the equation. Regardless, this remains one of the best close-by systems in which to search for evidence of life in general. Number 2. Scholz's star. This red dwarf is interesting because we have apparently already interacted with it. Located at about 22 light-years distant, this star wasn't discovered until 2013. After further research in 2015, it was announced that this star passed through our solar system's Oort cloud about 70,000 years ago. This star is thought to be a binary system, with the main star being a red dwarf and an orbiting brown dwarf, and they're similarly aged to the Sun, with a minimum age of about 3 billion years old, but could be as much as 10 billion. This star's encounter with our Oort cloud is a little disconcerting. The reason is that it may have disturbed the Oort cloud when it passed by, and that any comets disturbed from the cloud at that distance aren't here yet. Don't worry, they won't be here anytime soon. It's going to take nearly 2 million years for them to get here, but it's conceivable that they may do some damage to Earth. But we'll probably either be long gone by then, or advanced enough to mitigate any threats posed, or so we hope, though at this point, we have plenty of warning time. Number 1. Alpha Centauri, Proxima Centauri, and Proxima b. Recently, an old question about the closest group of stars to us was answered. The question was whether Proxima Centauri, the closest star to the Sun, was actually a member of the Alpha Centauri system, or was just a free agent passing close by that system. It was found, however, that it is indeed a member, and is gravitationally bound to those stars. The main star system itself is called Alpha Centauri, which is really 2 stars. These stars are quite famous, but oddly they usually aren't mentioned under their official actual names, Rigel Kentaurus and Ptolemy. They are both Sun-like stars, one being Class G, very much like the Sun, and only a little larger, and the other is Class K, which is smaller and cooler. While these stars may be of interest to a future humanity due to their proximity and similarity to the Sun, the third member of this system is of particular interest right now. Orbiting somewhat distantly from the main pair is the red dwarf Proxima Centauri. This is actually the true closest star to the Sun, at just 4.24 light-years. This star has a known planet, thought to be a bit larger than Earth, within its habitable zone. This planet, known as Proxima b, is of great interest in both the search for life on other worlds and the study of exoplanets due to how close it is. But there may be other member planets of the Alpha Centauri system. In 2013, an apparent transit of a planet was observed at Alpha Centauri b. This would not be a nice world if it exists, since it would orbit very closely to the star to the point of lava lakes on the surface. Models suggest that other planets could be in the main system, and given the similarities of these stars to the Sun, and the fact that Proxima Centauri may have played a role to send cometary material towards those planets early on, potentially delivering water, means that not only are they the closest stars to us, but are among the most interesting, very much so for a future humanity spreading into the galaxy, but also remain some of the best candidates close by for the search for life right now. The universe, if nothing else, is full of very big things. Planets can be enormous, as can star systems, galaxies, and so on. But how big do things really get in the universe? The answer is mind-blowingly huge, so here are 10 enormous cosmic structures. Number 10. The Laniakea supercluster. One particularly interesting giant structure in the universe is interesting specifically because we're a part of it. Known as the Laniakea or local supercluster, this structure contains about 100,000 galaxies, and the Milky Way is one of them. Unfortunately, though, this supercluster is not believed to be gravitationally bound and will someday disperse. The local supercluster is immense, stretching over 500 million light years. It's actually subdivided into 4 parts, previously thought to be separate superclusters in their own right, but are now known to be linked. The Milky Way lies in the Virgo supercluster part, and it's further subdivided into a series of clusters and groupings, though we'll never know exactly how many because they lie in what is known as the zone of avoidance, which is the disk of the Milky Way that obscures anything behind it from our perspective in visible light. Also hiding in the zone of avoidance is the focus of our local supercluster, known as the Great Attractor. We can't see it in visible light, but we can see its effects and observe it in other areas of the electromagnetic spectrum. It seems likely that the Great Attractor is yet another very dense supercluster acting on everything around it gravitationally. But there is an anomaly here, or at least a potential one. Standard cosmological models suggest that the motion of galaxy clusters in respect to the cosmic microwave background radiation should be random. However, some data suggests that it's not, and that some process is causing a flow, termed dark flow, in a common direction. It's debated whether dark flow actually exists, with contradictory measurements going both ways, but there is an interesting clue here should it prove to exist. One idea is that what caused it was interactions between parts of the universe that are now beyond the observable universe, but were once very close before inflation in the Big Bang. Another possibility is that it's being caused by a sibling universe, suggesting a multiverse, or some region of spacetime that is very different from what we know and understand. Number 9. The Hyperion proto-supercluster. Looking deeply into space is the same as looking back in time. The further an object is, the further back in time you see it. Eventually, if you look far enough, you see back to the earliest objects in the universe. Not quite yet a supercluster from our perspective, the Hyperion proto-supercluster is the earliest known example. We see the structure at roughly 20% of the age of the universe, or a distance of about 11 billion light years. It's expected over time to develop into a full-blown galaxy supercluster from our perspective, though in reality it likely already is. We just won't see it for a very long time. This particular structure is also interesting because it shows a mismatch in the gravity the objects within it should have versus how it actually behaves, suggesting the involvement of dark matter. But it's dark matter interacting dating from the early universe, giving us one of the scant clues we have about dark matter, that it's been here interacting gravitationally with the universe for a very, very long time. Number 8. The local void. Just adjacent to our own local group of galaxies, known in this case as the local sheet, is a void, a huge one. At least 150 million light-years across, this structure's size was determined by a very isolated dwarf galaxy inside it, one of just a handful currently known to be in this void. This little galaxy is behaving strangely. It should be moving towards concentrations of matter, in other words, the galaxies at the edge of the void through gravity. And it is, but it's apparently moving too fast, invoking the involvement of dark energy in one hypothesis. To add to the mysteriousness of the void, it's also growing, with our local sheet essentially rushing away from the void's center. And to add further mystery, the local void appears overall to have fewer galaxies than standard models would suggest. Why that is unknown. What is known is that galaxies do not like to be in that void. Number 7. The upper limit. While not a structure in itself, what could be called the upper limit determines how large structures in the universe can be in principle. Many of the vast superstructures on this list are products of just how the aftermath of the Big Bang played out. Originally, there was very little difference in density other than slight variations in the universe. But as time marched forward, those tiny variations were amplified by the effects of gravity, forming galaxy clusters, superclusters, and the voids in between them. But there is a limit to how big those structures should be. And herein lies a mystery. Standard models in cosmology state that the expansion of the universe should limit gravity's clustering effect on objects, and that we should see a limit to the size of these structures. Problem is, there are apparent structures in the universe that exceed this limit. many of which are on this list, and some of them do it by a lot. This should not be, but apparently is. What's at play here could involve dark energy, but in a really strange way. It's usually assumed that dark energy is uniform throughout the universe. If it's not, however, and it can accumulate, then the repulsive force it exerts could push matter away, allowing for larger than expected structures. Or, alternatively, there could be something we don't know about gravity. And there's more to the story than what general relativity paints. But there's always room for error in this. Measuring distances in the cosmos is a tricky thing, and as you'll note, many of the apparent largest structures in the universe remain unconfirmed. But it's an interesting thought that if something ever is confirmed that violates our models, then we have a fundamental problem with our models of the universe. Number 6. The SSA-22 protocluster. This structure is rather odd in just what makes it up. It's very distant, about 12 billion light-years out, meaning that we're seeing the object in a very early state. Not only are there star-forming galaxies present in the structure, but also objects known as Lyman alpha blobs. These are enormous bubbles of gas that can be so large that they measure twice the diameter of the Andromeda Galaxy. What causes these huge blobs is ultimately unknown, but it has been advanced that they are the remnants of giant supernovas that occurred among the earliest giant stars in the universe. The structure itself lines up along 3 curved filaments and is actually really dense, with all of the objects in the structure packed closely in when compared to the rest of the universe. Further study of this object will likely yield clues about how our own galaxy formed, but may also be among the first structures in the universe to have formed, yielding clues on the conditions of the early universe. Number 5. The giant GRB ring. One of astronomy's most mysterious phenomena, gamma ray bursts, seem to hint at something potentially even more mysterious. In 2015, it was discovered that a ring of 9 gamma ray bursts seemed to hint that they were in some way related. This structure, if it's really there, is amazingly distant at over 9 billion light-years away, with a diameter of 5.6 billion light-years, making it one of the largest known structures in the universe. The main question is if the gamma ray bursts are actually related or only appear that way. The distribution of gamma ray bursts in the observable universe would say that such an arrangement would be highly unlikely. If it does exist, it's likely to be a huge structure of galaxies with active star-forming regions being linked to the gamma ray bursts. Number 4. The Bhuta's Void. Also called the Great Nothing, the Bhuta's Void is an area of space about 330 million light-years in diameter. It's roughly spherical and very distant from us at about 700 million light-years away. What's noteworthy about this structure is that it's nearly empty, containing very few galaxies, at most a few thousand across the entire void. If you happen to be inside this void in one of those scant few galaxies, it would be a very strange place to exist. If you were at the center, you would need a very large telescope to even know that other galaxies existed. Just how the void came into being is an open question, but there is a good possibility that it resulted from the merger of a number of smaller voids, sort of like bubbles coalescing into larger bubbles. And indeed, there are some features of the arrangement of the galaxies that are in the void that seem to bear this out. Number 3. The CMB cold spot. This is one of those cases of a structure, at least one of sorts, that really shouldn't exist yet it does. The CMB cold spot is an enormous area of the cosmic microwave background radiation that is unusually cold, and also unusually large for what is expected from the CMB. One explanation for it is that it's simply formed from quantum fluctuations during cosmological inflation. The problem is that mechanism is unlikely, though it's not impossible, to form such a large cold spot. Other options include the presence of a supervoid in space in between us and the CMB, but that supervoid would have to be enormous, perhaps the largest structure in the universe, to account for it. One more controversial idea is that the cold spot is an imprint of a parallel universe that was once entangled with ours until separated by cosmic inflation. This concept is actually observationally testable, and if it ever is, then it will be the first indicator that a parallel universe to our own exists. Number 2. The huge LQG. This is a very different kind of structure, if indeed it's a structure at all. The huge LQG, or huge large quasar group, is made up of 73 quasars spread over a whopping 4 billion light-years at about 9 billion light-years from Earth. Quasars are very odd, distant, and energetic active galactic nuclei, driven, it's thought, by the activities of supermassive black holes. This structure has been a subject of dispute in recent years in that it may just be illusory or an artifact of how the original study was done that discovered it, though recent work seems to suggest that it does indeed exist, and large groupings of quasars are known, just not ones quite this large. But there's a problem. There should be a limit on just how large such a clustering can be. This gets into the cosmological principle, the assumption that when looking at large scales, the universe looks the same no matter where you are. This has never been demonstrated, so it remains an assumption. An important one, since Einstein depended on it in his work, which tends to hold up quite well to observation. If the huge LQG indeed exists, then the cosmological principle is then in question. What this means for our understanding of the universe remains to be seen. Number 1. The Hercules Corona Borealis Great Wall. This structure is known not only for its immense size, if it indeed exists, but also for a link to another strange phenomena in the universe, gamma ray bursts. This enormous structure is the largest known structure in the observable universe, spanning about 10 billion light years and containing billions of galaxies. Researchers working with gamma ray bursts noticed a strange, rather implausible clustering of gamma ray bursts in one area of the sky. At first, it wasn't clear how this could be. As it turns out, the best explanation for the concentration of GRBs is that an underlying structure exists, known as the Hercules Corona Borealis Great Wall. This formation may be a region of dense star formation, thus leading to a higher incidence of gamma ray bursts, which are thought to be caused by stellar collapses and neutron star mergers. Our galaxy is also a member of a huge supercluster, but the Hercules Corona Borealis Great Wall is on the order of 30 to 50 times larger. That's thought to be improbable in this universe, leading to some question of whether this structure really exists or is a product of observational issues or some other phenomenon. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently perplexed. Life on Earth sometimes shows convergent evolution, which is why only distantly related creatures like sharks and dolphins resemble each other. Useful features are useful features, and we may well see the same kinds of forms in alien life. Feet are also useful, so aliens may have them. If those feet are rather large, then I can't rule out space Bigfoot. Very disconcerting, and be sure to check out my books at your favorite online book retailer, and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live. While there are many mysteries within astronomy that remain unexplained, there are some that remain somewhat obscure, but very strange indeed. So here are 10 obscure but perplexing unexplained mysteries of the universe. Number 10. The Kuiper Cliff. The far outer solar system is a place that was once thought to be a frozen wasteland of sparsely distributed material where not much generally happens. This has turned out to not be the case. With the flyby of both Pluto and Ultima Thule and the discovery of numerous minor planets in the Kuiper Belt, things have gotten very interesting indeed. And there's even the possibility of at least one full-on planet and possibly two lurking out there, Planet 9 and Planet 10. Mysteries galore. One of these mysteries is lesser known, however. It's called the Kuiper Cliff, and it seems that at a distance of about 47.8 astronomical units, the number of objects present in the belt abruptly drops off. This may either be a cliff altogether or just a broad gap, and there may be more objects further out. This situation defies all predictions, which had previously stated that the number of objects out there should actually increase rather than drop off before you leave the belt entirely. The reason for the cliff is unknown, but it may be that matter that far out was simply too rare to be able to accrete into large objects. Or, as one hypothesis states, it's possible that an unseen, roughly Earth-sized planet cleaned the area out. If so, that planet is presumably still out there, distinct from the possibilities of Planet 9 and 10. Do 3 undiscovered planets lurk in the outer solar system? Number 9. Space Roar. In 2006, NASA's Arcade instrument detected something really bizarre. The instrument was designed to be mounted on a very high altitude balloon in order to get above most of the atmosphere and study how the earliest stars in the universe heated it up. In July of that year, they detected a very strange radio phenomenon that to this day remains completely unexplained. Called space roar, this radio signal was 6 times stronger than what was predicted before the experiment launched. It's loud, so to speak, and every explanation for it to this point has fallen flat. This included abundant radio galaxies, which are not abundant enough to account for it. Gas in the outer reaches of the Milky Way was also ruled out, as was noisy primordial stars. All that's known is that the source is very far away, dating from the early days of the universe. Past that, it's an unknown. Number 8. The flyby anomaly. One of the stranger phenomena when dealing with the normally clockwork-like physics of the solar system is the flyby anomaly. One of NASA's major tools in sending out probes to explore bodies in the solar system is flyby gravity assist, where a close flyby of a planet gives a spacecraft a boost in speed. In principle, this process should be completely predictable in its behavior. Trouble is, it isn't. Instead, what happens is that the spacecraft gain greater speed than they should, and it's been seen in multiple spacecraft using multiple techniques, but it also doesn't always happen. The phenomenon was first noticed with the Galileo mission in 1990 as it swung past Earth. Yet, when it flew by Earth again in 1992, the anomaly was not seen, though it may have been present but just lost in the noise as that flyby was quite close. Other spacecraft who have experienced the effect include Cassini-Huygens, Near, and Rosetta, yet Messenger did not see it. But Messenger was different in that it passed at the equator, where all the others did not, which might suggest that whatever is responsible has to do with the Earth's rotation. Other spacecraft that did not see it was Juno in 2013 and a 2009 pass of Rosetta where the anomaly was specifically looked for but not seen. Possible explanations include a dark matter halo around Earth, problems with the network used to receive data from the spacecraft, or some misunderstanding within physics, though none of them seem particularly satisfying explanations, and the flyby anomaly remains a mystery. What else remains a mystery is that the effect is not usually noted with other planets. Whatever it is, Earth seems special in this regard. Number 7. M82X2. This object is quite the enigma. It shines at about 100 times brighter in X-rays than our theory suggests that something of its mass should be able to do. It was originally thought to be a black hole, but it isn't. Observations indicate that it's actually a pulsar. But if it is, then 2 questions arise. How can it remain stable, and where did it come from? The basic problem with this object is something called the Eddington limit, which places an upper limit on the brightness that something of a given mass, such as a star, should be able to produce. This pulsar simply violates it, very much so. And while there are a handful of other stars that also seem to violate it, the limit is really more of a guideline than any kind of a real limit. They don't do it to this extent. There must be something very special and crazy going on with this pulsar. But no one's thought of anything good yet to explain it. The best guess is that the geometry of material falling into this pulsar along its magnetic lines is somehow rare and different than normal pulsars, producing an effect that appears to violate the Eddington limit, but actually probably doesn't, at least as that limit is set up. It's just some kind of odd and very special circumstances producing a kind of illusion. How this situation came to be is unknown, and given that M82X2 is the only known instance of this, then it must be some very rare circumstances indeed. Number 6. The lithium problem. While the element lithium famously tends to be the least interesting of the elements produced by the Big Bang, there is a mystery surrounding it. Of particular interest is the isotope lithium-7, which current models of the Big Bang all predict that it should be 3 times as abundant in the universe than it actually is. This is strange because these models predict other isotopes of other elements very precisely against what is observed. There are also other odd observations regarding lithium in the universe. For example, stars that are known to have planets seem to have significantly less lithium than stars without planets. There may be a mechanism for this. It could be that gravity exerted by the planets on a star might cause the lithium to sink into the core where it is destroyed. This has led to an interesting possibility that a new way of detecting planets around stars could lie in studying lithium abundances in a star. Why lithium-7 is so deficient in the universe is not understood. Explanations put forth include unforeseen reactions during the Big Bang nucleosynthesis. Others include the involvement of dark matter. But given that dark matter has never been directly detected, and its nature only hypothetical, it's anyone's guess what might be happening there. But this is not the only time that lithium-7 has surprised us. During the Castle Bravo nuclear test in 1954, a detonation 2.5 times the size of what was predicted occurred. This was because the lithium-7 involved in the bomb's reaction was thought to be inert and would not contribute to the reaction. This was a huge error, and the Castle Bravo detonation of 15 megatons remains the largest nuclear test the United States has ever conducted, albeit unintentionally. Number 5. How big is the universe? Within the universe exists a certain reality that's hard to fathom. There are parts of it that we, as humans, will never know and interact with. Entire galaxies and groups of galaxies, as far as we know, we have no hope of ever knowing about. This is due to the speed of light and the expansion of the universe. Eventually, over great distance, you get too much expanding universe for the speed of light to ever overcome it. So the assumption is made that there is more universe than what we can actually see, which we term the observable universe. The unobservable universe is, well, not observable. So it may be that we can never know how large it actually is. You can change this by traveling at relativistic speeds. Parts of the universe you are not able to see should come into view, but you are limited by the speed of light, so you can't ever overcome it enough in order to see the entire universe. This leads to an interesting conundrum. The question has to be asked if the universe is finite or infinite. If finite, then it may only be a small amount of the universe that we cannot see, or it may be significantly larger, or it could be infinite. We'll probably never know which is the case, but if it's infinite, then if you travel far enough, one might come across near carbon copy Earths, full of near carbon copy people, right down to you and me. If that's the case, then the "are we alone" question takes on a completely new meaning. Number 4. Why is the sun's corona so hot? One problem in solar physics is why the sun's corona, its atmosphere, is millions of degrees Kelvin hotter than the sun's actual surface. This problem stems back to the early days of solar physics. Certain lines were seen in early spectra taken of the sun that led some researchers to suspect that they were actually seeing the absorption lines of an unknown element on the periodic table. It was actually even named coronium, but this turned out to not be the case, and in fact reflected known elements that were in very intense states of ionization. This in turn led researchers to conclude that the sun's corona was ridiculously hot, yet the surface of the sun is, in comparison, much cooler. The problem lies with the second law of thermodynamics, meaning that heat coming from the sun's surface can't flow directly to the much hotter corona enough to account for its temperature. In turn, this means that there must be another mechanism involved for transferring energy to the corona. There have been a number of theories to explain this that have been advanced, including a recent one that seemed to reveal braid-like structures in the corona. This led to a hypothesis that magnetic reconnection and these braids unraveling might produce the heat, but ultimately no one knows why the sun's corona is so hot. But we may be near to an answer for this one. One of the objectives of the currently active Parker Solar Probe is to look into this mystery, and we may well find an answer. Number 3. Baryon asymmetry. We can make antimatter, but it's not easy or cheap. In fact, it's one of the most expensive substances on Earth, but we can do it, and nature does it too. There is a fountain of some sort near the center of the galaxy that's literally shooting out positrons that annihilate when they hit normal matter, to the tunes of millions of tons of the stuff being out there at any given time. Antimatter exists, and we and nature can create it. But there's a deeper problem. While we do see antimatter being created in nature and in the laboratory, there seems to be no reason why the Big Bang should not have created just as much antimatter as matter. Baryonic matter, or normal matter, seems to have been made asymmetrically to antimatter. Trouble is, there's no reason why this should be. Neither the Standard Model nor Einstein's general relativity give any kind of reason why this arrangement should be. Instead, the Big Bang should have produced equal amounts of both, and they should have annihilated on coming into contact with each other. There must have been something that favored baryonic matter and produced some quantity more of it than antimatter. What this mechanism was and how it all came to be is unknown, but in the end, if you think about it, it digs directly into the origin of matter itself, something not often discussed. Matter can lead to life, and life leads to us. Had things been different, we could easily have been born of antimatter rather than baryonic matter, as the two are identical other than charge. Could there somewhere be anti-life? Number 2. Ultra-high energy cosmic rays. One of the most mysterious and rarest phenomena we detect coming from space are known as ultra-high energy cosmic rays. These rays enter our atmosphere at very extreme levels of energy, the most energetic particles known, as much as 1,000,000 times that which we can produce in an atom smasher here on Earth. Problem is, the energies observed in these particles shouldn't happen. The real question here is what's producing them? It must be some kind of extreme environment, such as a starburst galaxy. But if they are being generated by something very active but distant, such as active galactic nuclei, then there's a huge problem. They should only be able to travel at these energies for about 150 million light years. Past that, they would be slowed due to the interaction of the particles with the cosmic background radiation. Most extragalactic sources would seem to be too distant. Yet we see them. Possible causes are that the sources for these particles are actually close, but seem a bit less likely, such as neutron stars with very strong magnetic fields. But if that's the case, why would the sources be so rare? Another are supernovas, accelerating the particles to these energies. More exotic options include dark matter being converted by black holes into normal protons. But there's another problem. It seems that the higher energy the particle, the heavier it gets. This means that at high energy, the particles are protons, but at higher and higher energies, they are helium nuclei, then carbon, and so on, with one hypothesis stating that they might even go as heavy as iron. This is the exact opposite of what is expected. And more, heavier particles should be subject to even more scatter than normal cosmic rays, which tend to be so hopelessly scattered that their sources can't be determined. Yet, with ultra-high energy cosmic rays, the scatter is much less, opening the possibility of eventually determining a source. And it gets stranger. For these particles to exist, the source must be producing them close to its top possible energy. It's unknown what that kind of object could be. But secondly, there must be something about the circumstances of travel through space that allows these rays to maintain their energies. Another oddity is that at the exact energy that normal galactic cosmic rays stop, the ultra-high energy cosmic rays start. This may just be a coincidence, or there's either something wrong with our models of how particles in general behave, or how we detect them in the Earth's atmosphere. Or it might be even more exotic, and that the highest energy rays aren't really heavier nuclei, but protons just acting like it. This gets into even more strange and speculative territory, such as the protons forming mini black holes in their initial collision, making them appear heavier, but that requires things we have no real understanding of yet, such as large extra dimensions of the universe, which we have no indication even exist. But in the end, no one knows what causes such high energy particles in the universe, and if they do turn out to be from distant sources, then we will have an even larger mystery on our hands, one that might even violate the laws of physics as we understand them. Number 1. Is it all even real? There's no question that the universe in some respects is a very strange place, one that we very well may never understand completely, and some aspects of it are so strange that it's led to some thinking that the universe may not be as it seems. The first take on this is a very old idea going back to Descartes in its original form. The idea is a philosophical one rather than a strictly scientific one. And in a nutshell, it states that if you were a brain in a jar with all sensory input about the universe fed to you, say through electrodes or some other technological means, then you may not ever know that none of it is real. To you it would seem so, but it wouldn't be. Another take is that it's all a simulation, and that we are all some sort of intelligences embedded within it. In this case, strange possibilities come into play. Perhaps we are humans of the future simulating ourselves, and the universe as it was in the past in what's called an ancestor simulation. Or worse, that we are a simulation being concocted by another thought experiment, a Boltzmann brain. In this concept, if you wait long enough in an infinitely existing universe, consciousnesses, or even gigantic sentient supercomputers capable of simulating a universe, will eventually and randomly come into existence. Imagine if you suddenly woke up to find yourself in an ancient, dark, and very dead universe. Trying to figure out the nature of it, or just to avoid the infinite darkness, you might just try to simulate a universe or something like one. Are we the fever dreams of an utterly alone Boltzmann brain? But in the end, those are really more a matter of thought experiments than anything else. But one last possibility does come from science. We know that on the quantum level, particles behave like waves and exist in quantum superpositions until they are forced to collapse through observation. So the question is, does the entire universe itself have a wave function that's being collapsed? Some scientists suspect yes, others suspect no. But if it does, what would happen to the universe if there was no one to observe it? At that point, would the universe even matter? Our galaxy contains a vast number of stars, with some estimates going as high as 250 billion individual stars, some like our own, some vastly different. Often these stars are run-of-the-mill and very predictable, but sometimes stars can end up in situations or go through strange circumstances that make them very different from most other stars. So here are 10 of the Milky Way galaxy's most interesting stars. Number 10. Mira. The Mira star system is actually a binary system with a large pulsating red giant, Mira A, and a much smaller white dwarf companion, Mira B. To the naked eye, Mira A is a variable star on an 11-month cycle that essentially disappears and then reappears. This was known probably since ancient times, but certainly by the 16th century. What's going on in this system is that Mira A, the red giant, is shedding material into space. Some of this material then accretes around Mira B. This shedding of mass creates two interesting phenomena in the system. First, the system itself is shedding material into the interstellar medium, giving it the superficial appearance of a giant comet, though the trailing material stretches for light years, much greater than that of a comet's tail. The second phenomenon is that there appears to be a protoplanetary disk formed around Mira B from the ejected material from the red giant. This is strange since protoplanetary disks are typically found around young stars rather than dead white dwarfs. This could mean that new planets are forming around a dead star, something not known to happen before it was discovered at this star system. Number 9. SAO 206462. While looking superficially like a comet is a trait of Mira, looking superficially like a spiral galaxy is a trait of SAO 206462. This is a very young star surrounded by a protoplanetary disk, which is not unusual for young stars still forming planets. But what's unusual here is the structure of the disk. It's arranged as spiral arms. This star is relatively close at only 460 light years, and its protoplanetary disk itself is huge, about twice the size of the orbit of Pluto. What causes it to exhibit spiral structure seems to be due to recently formed planets within the disk being arranged in such a way as to shepherd and shape the disk into spiral arms through the action of gravity. Each arm of the spiral is being influenced by a planet, and there are at least 2 in this system. These planets are still forming, and the entire feature won't last long in geologic timescales. Eventually, the debris disk will thin out as material accumulates on the planets of the system until the spiral structure, and indeed the visible disk, disappears. Number 8. BPM 37093. Located in the constellation Centaurus, BPM 37093 is about 50 light years from Earth. This star was originally thought to be a white dwarf, but it was later found to be incredibly dense. It has a little bit more mass than the Sun, but it's all compacted down to about a third of the size of the Earth, making it effectively a crystallized star. White dwarfs in general are believed to predominantly be composed of carbon and oxygen, and a prediction from the 1960s said that cooling white dwarfs should begin to crystallize. BPM 37093 was found to be pulsating as a variable white dwarf, and this has allowed scientists to test this crystallization concept. It turned out to be correct, and in the case of BPM 37093, it was found to be as much as 90% crystallized, though estimates of this vary. So when you start subjecting carbon to high pressure and it begins to crystallize, you get diamond or something like it. So it could be said that this white dwarf, at least at some depth, essentially turns into a giant diamond. At that point, can it really still be called a star? Number 7. HE 0437-5439. This star is a relatively normal, young, B-type star, except that it appears to be moving extraordinarily fast, so much so that it's ejecting itself from the Milky Way entirely. The speed of the star is about 723 kilometers a second, or 1.6 million miles per hour. How this star ended up screaming across space isn't clear. It appears to have been part of a binary system originally that encountered a supermassive black hole near the center of the galaxy. Problem is, this would have had to have happened about 100 million years ago, yet the star itself is only about 20 million years old, if that. So the star may be a product of a merger of 2 binary stars that had themselves been previously ejected, though it's not entirely clear just how that happened. but may have been a product of what was originally a triple star system that encountered the supermassive black hole at the galaxy's center. One star was captured, and the other two ejected, which then merged at some point to become the Type B star we see now. Number 6. MY Camelopardalis. Stellar mergers are not unheard of, but actually catching a pair of them in the act of merging is relatively rare. Yet, that's exactly what we're seeing with the MY Camelopardalis star system. Originally thought to be a normal variable star, it was found that MY Camelopardalis is actually a contact binary system, where one component is eclipsing the other. Eclipsing binaries aren't unheard of either, but these two stars are so close that their atmospheres are touching. The two stars are both hot, blue O-type stars, much more massive than our Sun, about 32 and 38 times respectively. Eventually, these two stars will fully merge and form a supergiant star, confirming an older hypothesis about how such stars are formed. Number 5. UY Scuti. In a galaxy with a population of very large stars, just how large do stars get? The star UY Scuti is one of the largest known stars in terms of radius. This star is enormous, with some estimates as high as 1,700 times bigger than our Sun, and 3 times bigger than the famous red giant Betelgeuse. And it's thought it's going to die in a similar way. It's thought that this star has begun to fuse helium along with a shell of hydrogen fusion. As it begins to fuse heavier and heavier elements, it will eventually hit iron. At that point of no return, the balance between radiation pressure and gravity will change, causing a core collapse supernova. Number 4. APEP. APEP is a triple star system containing a hot supergiant and a pair of really strange and violent stars known as Wolf-Rayet stars. These stars are very different from normal stars in that they are fusing elements heavier than hydrogen and helium, yet are still fusing hydrogen and helium, leading to a layered effect of different kinds of fusion. These stars are intensely bright, essentially being naked fusion cores as their outer layers are blown off into space. The Wolf-Rayet stage in a star's life is short-lived, and a supernova is expected in this system. But there's something else that's expected here as well when that happens: a gamma-ray burst, making the APEP system the first known progenitor system for that phenomenon. Number 3. Vega. This star is noteworthy for being close to our Sun, only about 25 light years, but also for being the 5th brightest star in the night sky, and for its appearances in science fiction, such as Carl Sagan's Contact. But in its own right, the Vega system is interesting. Vega was one of the first star systems suspected of having a debris disk, and in the days before exoplanets were confirmed to exist, suggested that since material was surrounding the star, then material for forming planets and asteroids was common in the universe. Thus it was likely that planets abounded. This has since been shown to be true. But there's another strange aspect of Vega. It's squashed. The star rotates very rapidly, and due to centrifugal force, the star is somewhat flattened out at the equator and compressed at the poles. This also causes the star to be hotter at its poles than at its equator. It's unknown if Vega actually has any planets. This is still a subject of debate. But if it did and you were standing on one, you would actually see the elongated state of this star visually. It's that apparent. Number 2. VVV WIT-07. The study of light curves taken of stars in recent years has yielded a treasure trove of information about the universe. The Kepler spacecraft alone discovered several thousand exoplanets through this method, and successor instruments continue to do so. But there have been surprises, such as the difficult-to-explain star KIC 8462852, or Tabby star, whose dimming events still aren't fully explained to this day. But there have been other strange stars exhibiting unexplained dimming that have been found. One such star is VVV-WIT-07, with the WIT part standing for "What is this?" This star is similar to the dimming events at Tabby's star, but exhibits much deeper events. One event actually dimmed the star by 80%, far higher than the deepest observed with Tabby's star, which was about 22%. Another similar star, but not quite, is known as J1407, though that star was explained through a planet with an enormous ring system that was blocking the light. This does not appear to be the case with VVV-WIT-07, nor does it appear to be a binary system, which might also cause dimming events. It's still completely unknown what's going on with this star, and there are a lot of possibilities, including massive dust clouds. but nothing quite fits the bill. But one thing is clear. Strangely dimming stars don't appear to be very rare in the galaxy, and new ones are found regularly. It may well be that one day we find dimming that's not being caused by nature, but rather the activities of an alien civilization. Number 1. The Sun. For something so familiar to the point that the activities of the whole of humanity, everyone that's ever lived, depended on it, the Sun is actually not that familiar of an object to the rest of the galaxy. Our Sun is a type G quote-unquote yellow dwarf, though it is neither yellow nor is it particularly small for a star in comparison to the much more numerous and much smaller red dwarfs. Type G stars make up only about 7.6% of the main sequence stars in the galaxy, but here's where the Sun starts getting rare. Stars like the Sun tend to be part of binary systems, or at least about half of them. Our Sun appears to have never had a companion, though this is still debated. In comparison, the closest G-type star to the Sun, Alpha Centauri A, is part of a triple star system. This generally presents an issue for planetary systems, at least ones like our own, and nothing quite like the solar system has ever been seen around other Sun-like stars yet. But perhaps most conspicuous is how stable and quiet the Sun is when compared to stars like it. While it has flares and such, it's nothing compared to how active some stars like it tend to be. This lack of variation in the Sun's brightness over time may have played a part in the evolution of life on Earth, which as far as we know is the strangest aspect of this star. It didn't just present the conditions for life, it allowed for a full-fledged civilization to appear on one of its planets, which is likely something that takes a very long period of stability to realize. That set of conditions, which are not fully yet understood, may well make the Sun one of the strangest and most interesting stars in the universe. In celebration of the Halloween season and a continuing tradition of this channel going back to the early days, here are 10 spooky things that the universe does, or may do, that are currently invisible to us and we have no control over. Number 10. Dark matter. While studying galaxies, it became evident to scientists that the visible material contained within them couldn't account for the observed gravitational effects. This led to a conundrum. Either something was fundamentally wrong with our understanding of gravity and physics in general, with gravity already being murky territory, or there was some unseen, invisible, almost entirely non-reactive material in the universe that not only reacted only through gravity, but apparently constitutes the bulk of matter in the universe, as much as 85%. While the existence of dark matter is fairly widely accepted within physics, it's not universally so, and a small contingent of scientists believe that instead there may simply be a problem with our physics on huge scales. This would not be unheard of. Einstein's relativity came out of small discrepancies found within classical Newtonian physics. But if dark matter does exist, it's thought that it may be made up of non-baryonic subatomic particles that have yet to be discovered, and they would be very difficult to discover indeed if they only interact with everything else through gravity. Gravity on the subatomic level is unbelievably weak, but it's interesting to think about the idea that you yourself, right now, are surrounded by an invisible halo of non-interactive material that we know almost nothing about, and there's a chance that we never will. Number 9. Dark energy. Just a few decades ago, it was assumed that the expansion of the universe would eventually slow and stop due to gravity. Subsequent observations by the Hubble Space Telescope blew that out of the water and indicated that in the early universe, the expansion was actually slower than it is today. The predominant explanation for this is dark energy that drives the expansion of the universe to faster rates, and based on observation, it can be estimated how much energy is involved. As it turns out, a lot. It's estimated that about 68% of the universe is dark energy. Dark matter is about 27%, and only about 5% is normal matter, which actually means that normal matter is actually the abnormal part of the universe. But that's about all that is known. What this energy is and what it might imply are still mysteries. Possibilities are that it is energy inherent to space itself. Space, while it may seem like the ultimate nothing, is actually more of a something, and may be able to have its own energy, which would be spread evenly across it. Since space is expanding, or in other words being created, more of this energy should come into existence as the universe ages and expands. What all this means, and even if we'll ever even know what dark energy is, remains to be seen. Number 8. The Great Attractor. Our galaxy is unfortunately very difficult to see through when you look straight at it through its plane. Step outside some night and look at the Milky Way. It stretches across the sky, and we see it as a member of that galaxy sitting out in a suburban location near a spiral arm. What's difficult is seeing through the galaxy from our perspective, as much dust, gas, and stars lay in the way. Behind that mess, however, is something that we cannot directly see, but we certainly see the effects of. It is the gravitational anomaly known as the Great Attractor. The Milky Way is located in a supercluster of galaxies. The center of this supercluster is obscured by the Milky Way, but shows evidence of something with a mass thousands of times the Milky Way lurking there. Astronomers see the effect of this anomaly in the motions and redshifts of galaxies and clusters of galaxies over a massive region of hundreds of millions of light years. They are being attracted towards the anomaly and seem to be being affected by a second phenomenon called dark flow, a non-random acceleration towards the attractor above what gravity might be doing alone. More recent work suggests that the attractor is a huge cluster of galaxies at the center of the greater cluster, not an unexpected state of affairs. But ideas like dark flow seem like an open door for further future mysteries regarding the movements of galaxies. Number 7. Aliens and the unobservable universe. Depending on who you ask, intelligent life in the universe is either very, very rare or not. On the one hand, there's no reason that Earth should be special, and there's no reason that we should be unique. Quite the opposite. Odds are there are, were, or will be other civilizations in the universe, given the sheer number of chances for it to happen. After all, there are an estimated 1 billion trillion stars in the observable universe alone, and that's just the observable universe. We can only see part of it, and we don't know how big it actually is, and it could even be infinite. In which case, there aren't only aliens, but copies of you, or someday will be, almost exactly the same, located an infinite amount of times across an infinite universe. Same goes for any alien civilizations that might be out there. Point is, it doesn't seem likely that we would be alone whether the universe is infinite or not, but wherever we look, we have yet to see a single shred of irrefutable evidence of an alien civilization. Yet, the fact that we exist shows that such things are possible. This inevitably leads us to the Fermi paradox, the question of where is everyone? Solutions to this range from the odds being such that civilizations within a single galaxy rarely exist at the same time, or that advanced alien civilizations don't look like what we envision them to, or simply that the aliens are hiding their presence from us, along with tens of other plausible solutions to the paradox. But say they're simply hiding. Do they just wish to not interact with us? Or are they waiting out there for us to venture into space? If so, what are their intentions? Number 6. The invisible death from outer space. About 440 million years ago, a mass extinction event occurred on planet Earth that seems to have been very different from the other major mass extinction events that have happened here. While there are a number of hypotheses that might fit the cause of this extinction, one of the worst Earth has ever seen, one idea that's consistent with the beginning of the extinction cascade is that a high-energy gamma-ray burst originating from far outside the solar system almost instantaneously burned off half of Earth's ozone layer, exposing surface or near-surface dwelling organisms to very high levels of ultraviolet light, causing their extinction. One possible explanation for this is the occurrence of a hypernova about 6,000 light-years from Earth. While there is no solid evidence for this occurrence, it merely fits the bill. Future gamma-ray bursts within the Milky Way do pose a threat to life on Earth. There are actually several different identified types of gamma-ray burst, and depending on circumstances, there are two ways they can kill Earth life. One is the aforementioned rapid depletion of the ozone layer, but if coupled with a release of cosmic rays, they could irradiate the surface directly, essentially killing a large portion of the surface life of the planet through radiation sickness. This brings up a star known as WR104, which may pose a threat. This system, which is about 7,400 light-years away, is set to produce at least one gamma-ray burst within the next 300,000 years. If the relativistic jet from this burst is pointed at Earth, which there is some indication that it might be, then it could pose a threat to Earth and eventually cause a mass extinction, and we may never see it coming. Number 5. Panspermic microbes. The microbial world is notoriously difficult to see, at least without the right equipment. But it's very evident in such things as food spoilage and infections. But we also know that some of the microbes represent the epitome of resilience of planet Earth, with species that have been identified that can withstand very high amounts of radiation, orders of magnitude more than a human, and even species that can completely dry out and remain dormant for very long periods of time. Because of this resiliency, it has been suggested that microbes might be able to survive traversing space inside rocks, at least to other bodies in the solar system, and conceivably further. While no evidence of this has yet been seen, it's not that far of a stretch to suggest that life might have appeared on bodies like Venus or Mars just as easily as Earth in their past history, or for that matter bodies like Europa or even Titan. This opens up the possibility that microbes from another world might end up deposited on Earth unseen, or it's also possible that life on Earth originated from somewhere else and was transported here. Who knows where we are originally from? Number 4. Outside the simulation. One somewhat vexing possibility with the universe is that it may not be real in the sense of an actual universe, but instead is a simulation. On the one hand, it doesn't intuitively seem like one, and if it were a simulation, it seems rather expensive and wasteful. On the other hand, if it's some kind of ancestor simulation, an argument put forth by Nick Bostrom, that one of three things must be true. Either the number of civilizations that can create such a simulation is nearly zero, or the number of civilizations that choose to do something like that is nearly zero, and if not those, then it becomes likely that you do live in a simulation. So given that line of thinking, if it is a simulation, then what's outside it? Who created it, if anyone? Given that we're in here and all of that is out there, it's unlikely that we'll ever know. Number 3. Vacuum decay. The universe is permeated with quantum fields that essentially hold reality together. While most of these fields appear to be stable, there's one that might not be. It's the Higgs field and its associated particle, and they are what lend mass to the universe. What's uncertain about the Higgs field is if it's actually stable. Think of it like this. You are on a mountaintop holding a bowling ball. You roll the ball down the hill, but it becomes stuck, say in a small valley or ditch. There's plenty more mountain to go down, the ball just can't get there without something agitating it and getting it rolling again. That may be the case with the Higgs field, and it may be analogous to a false vacuum. It may appear stable, but it has more energy than it would like to have. This opens up the possibility of it eventually collapsing to a lower energy state. One way for this to happen likely requires an enormous amount of energy, but another is via quantum tunneling. Could the Higgs field tunnel spontaneously to a lower energy state? Possibly, and if it did, it would be the end of the universe as we know it. As the change in state propagated through the universe at the speed of light, it would leave in its wake a universe with fundamentally changed laws of physics. This might mean that matter as we know it can't exist at all, or chemistry may be dramatically altered, and any number of uncertainties might create an entirely new reality. But one thing is for certain, life almost certainly will not survive it. Number 2. The multiverse and many worlds. One of the most vexing questions within physics today is if there is more than one universe. Much of the reasons for this lies in interpretations of quantum mechanics, but another part of the reason for this thinking is that this universe, given the hundreds of variables and values that allow it to exist as it does, looks a bit strange. If a few things were off, then matter couldn't exist at all, or the laws of physics and chemistry might be radically different. Even the idea of time itself happening to move forward is an open question as to why. And all of this happens to come together in just such a way to not only allow the universe to coherently exist, but for intelligent life to exist within it. That problem goes away in the concept of a multiverse. In that event, there could be many or even an infinite amount of universes. Some might turn out like ours, the vast majority probably not. Some could even just be black expanses where nothing much happens, a fate that's thought to lie for our universe in the very far future. These hypothetical alternative universes take several forms, such as the aforementioned take on the multiverse, but also ideas such as the interior of black holes being gateways to other spin-off universes. But there may be more than that. There is also the many worlds interpretation of the universe, where other realities are constantly splitting off from the universe, leading to different paths determined even by the most minor deviations. There could be many versions of you that ate different breakfasts this morning, or chose a different pair of shoes to wear. While contentious, these interpretations end up more plausible in some ways than the idea of a single, perfectly tuned universe. Any way you cut it, the universe is just weird. Number 1. In the future, no one will see much of anything. We exist at a lucky time in the universe, one where we can look out and see stars and galaxies, at least part of the universe anyway, and it's probably a good thing that we're here to photograph and study it, because in the far future it will be next to impossible to see much of anything out there. As the universe ages, bright star formation will slow and come to an end. Only the very longest-lived stars, the red dwarfs, will continue on. But they are dim by nature, and as they become the sole functioning stars in the ever-expanding universe, the galaxies will disappear from the skies, as will the stars themselves. Any civilizations present during this era may not even know there's a universe out there at all. They would only see blackness, and their ability to do cosmology will be severely hampered. They may not even be able to find out how the universe began. This state of the future universe has an interesting implication. If one hypothesis is correct, we're actually very early in the game as far as civilizations go, thus providing a solution to the Fermi paradox, the question of where is everyone? This could imply that over time, the amount of civilizations will rise, and if old ones, such as ourselves, don't go extinct, there could be an explosion of intelligence in the universe more or less right about the time that the stars start blinking out. To these civilizations, the universe might mostly be a mystery, and they might never know how it all began. While many of the solar system's moons are prominently discussed, such as our moon, Europa and Enceladus, there are some moons in the solar system that are very bizarre in their own right, but not well understood. So here are 10 somewhat neglected moons in the solar system that are outright strange. Number 10. Io. While many of the moons of the solar system are notable for having liquid water oceans locked under ice, or for that matter, liquid hydrocarbons on their surface, there is another body in the solar system other than Earth that has liquid lava on its surface. It's wildly volcanic Io. The reason Io is so volcanically active is because of its proximity to Jupiter. The little world is so close that Jupiter's gravity flexes it, causing Io to remain very hot. Add that with Jupiter constantly bathing Io in radiation, and you have what must be one of the harshest environments in the solar system. Oddly though, Io is still a long-shot candidate for life. It's thought that it once had as much water as any of the other Galilean moons of Jupiter, significant amounts of it that likely had a liquid phase before it all disappeared, but it's not completely gone. It could still be present below the surface. As such, it has been suggested, though a long shot, that perhaps deep in a moist lava tube somewhere below the surface of Io there might be, or once have been, simple life. Number 9. Nereid. Nereid is a fairly obscure moon of Neptune, its third largest, only discovered in 1949 by Gerard Kuiper, the namesake of the Kuiper Belt. We don't know much about this moon. Voyager 2 passed close enough to take vague photographs, but nothing even close to high resolution. Water ice has been detected on its surface, and very likely rock, but that's about all we really know about the object itself. But there are oddities. One is Nereid's eccentricity, which is the highest for any moon in the solar system. At its furthest from Neptune, it is nearly 10 million kilometers distant. At its closest, it's just over 1 million kilometers. This may suggest that it's a captured object, perhaps a wandering Kuiper Belt object. But from what we know about its composition, it doesn't look much like other outer solar system objects, suggesting that it actually formed around Neptune. It could be that during the capture of the moon Triton, which was probably originally a Kuiper Belt object itself, Nereid's orbit was affected in the process to create the eccentricity. But there's another mystery here. Some observations since the 1980s show that Nereid varies in brightness on a scale of sometimes years, but at other times only a few days. Yet other observations don't show this. So whatever is causing it, it seems pretty chaotic. There is currently no good explanation for this. Number 8. Iapetus. The discovery of Saturn's moon Iapetus is noteworthy for how early it happened. In 1671, Italian astronomer Giovanni Domenico Cassini observed it just on the western side of Saturn. He assumed that as it orbited, it would reappear on the eastern side. It didn't as far as he could see, and it remained that way for several years. He'd see it on the western side, but not the eastern side. So he obtained a better telescope, and in 1705 finally spotted it much dimmer on the eastern side. In what was an amazing feat of early observational telescope astronomy, he determined that Iapetus has a dark side and a light side, and that the moon was tidally locked to Saturn. This turned out to be correct, centuries before detailed images of Iapetus could be had, and indeed the dark region is now called Cassini Regio in his honor. That aside, once we did visit Iapetus with several probes, the most in-depth being a probe named after Cassini, we found a very strange world indeed. Firstly, because of a highly inclined orbit, Iapetus would be the only large moon of Saturn where the rings would not appear edge-on, and thus would be easily visible, perhaps spectacularly so. Why this inclined orbit is the case is still a complete mystery. Iapetus is a very icy world, over 80% of it being icy, it's thought, and even seems to undergo landslides on its surface. It's heavily cratered, some of which are enormous, and why one side of it is dark and the other side is light is thought to be because of warmer areas of the moon sublimating and leaving dark carbonaceous deposits behind, with bright ice accumulating on the lighter side. But the oddest aspect of Iapetus is its huge ridge. This ridge is mostly contained to the dark region of the moon, but some mountain peaks seem to continue it somewhat into the bright region. Explanations for this range from Iapetus once having had a ring of its own that accumulated down onto the surface over time, or geologic processes that formed it, but none of the present proposed explanations for how this could have formed explain why it's so concentrated on the dark side. Number 7. Mimas. Saturn's moon Mimas would otherwise not be very noteworthy other than its superficial resemblance to the Death Star from Star Wars, but in this case its formation would have very nearly been the death of Mimas. The crater is the second largest crater in comparison to overall size of any known body in the solar system, other than another Saturn moon, Tethys. Given that Mimas is mostly made of ice, it's somewhat surprising that the formation of this crater didn't shatter the tiny world into pieces. But there are indications that this almost happened. On the opposite side of Mimas are what appear to be stress fractures in the ice that appear to be a result of shock waves generated by the impact. Number 6. Miranda. While it's not known just how Mimas managed to survive its giant impact, there is one object that may not have survived an impact at all and had to reform entirely from the pieces, or at least that's one hypothesis. It's Uranus's moon Miranda, and shows some of the wildest topography in the solar system, ranging from enormous canyons, the largest known cliff in the solar system, and very obvious broken terrain. What caused this is unclear, but hypotheses range from extensional tectonics, where liquid water froze beneath the surface, expanding and cracking the surface. There is evidence of past cryovolcanism, where a mixture of water and ammonia might have flowed in the past like lava does here on Earth. Cratering on Miranda's surface suggests a mostly, but not entirely, old surface, but the crater seemed softened, perhaps by that same cryovolcanism. It may also be that Miranda was torn apart and reformed in the past, but that hypothesis has been losing favor in recent years. Unfortunately, we haven't seen all of this tumultuous, unique world. Only one half of it has been imaged to date. What features we might find on the other side remain to be seen. Number 5. Dactyl. One perhaps surprising thing about moons in the solar system is that not all of them are bound to planets. In 1993, the Galileo probe on its way to Jupiter visited the asteroid 243 Ida. As the data from the spacecraft was being downloaded and analyzed, it was noted that Ida had a moon. Known as Dactyl, the origin of this tiny object seems to be linked with Ida itself, either forming when Ida did when a parent object broke up, or was formed from a piece of Ida during an impact. But the composition of both Ida and Dactyl are very similar, and indeed similar to the most common type of meteorite found on Earth, the common chondrites. One oddity, however, is that Ida showed itself to have been subject to weathering in space, a reddening of its surface, whereas Dactyl showed less of this kind of weathering. Why this is not well understood. Number 4. Ganymede. Jupiter's moon Ganymede is noteworthy not only for being the largest moon in the solar system, it's bigger than the planet Mercury and Pluto, it's also noteworthy in that it has a magnetic field. And that field is affected by what very well may be the largest liquid water ocean in the solar system, far surpassing Earth. Ice shell moons that have liquid water layers are common in the solar system, but Ganymede's circumstances allow for a very thick layer of liquid water. This may allow for a very unique situation, where rather than just an ocean per se, it may be several oceans stacked in layers separated by alternating layers of water ice in different crystalline states caused by temperature and pressure. This creates questions about whether Ganymede might be habitable all around for life, in that it might be habitable only at certain layers, or no layers, and it's hard to predict if any layers in between the ices might be habitable, as ice in different phases behaves differently than normal ice in your refrigerator, which floats in water. Denser forms of ice, however, would sink instead of float, and might form an ice floor at the bottom of Ganymede's oceans that might prevent interaction between the water and the rocky surface below, affecting the availability of nutrients. But the water at Ganymede does appear to be salty, so it's anyone's guess what might be going on down in that high-pressure environment. Number 3. Phobos' Death Wish. The moons of Mars are moons in the sense that they are in orbit of Mars, but not particularly impressive ones, and really are more like asteroids than anything else. But that may change. The moon Phobos, which is named after the Greek god and personification of fear, something that may well be relevant to any Mars colonists living on the planet in the future, is slowly moving closer to Mars. Sometime within the next 30 to 50 million years, one of two things is expected to happen. Either Phobos will fall into and impact Mars, which would probably be quite the spectacle and could form a huge crater, or it will be torn apart by tidal forces and turn Mars into a ringed planet for a time. This would be a very different look for Mars indeed, and interesting, because by that time Saturn may well have lost a significant portion of its ring system. That's if it happens at all. 30 to 50 million years is a very long time, and if the human species lasts that long, we may well have completely terraformed Mars into Earth too at that point, in which case Phobos and the other moon Deimos may well have long ago been converted into raw materials for space habitats. Would you live on a space station that was once a moon called Fear? Number 2. Epimetheus and Janus. In addition to acting as shepherd moons maintaining the sharp edge of Saturn's A-ring, these two moons do something very unusual. They swap orbits. The moons are on two very similar orbits, one slightly further out than the other. The closer orbit is slightly faster than the outer orbit. As they near each other through gravitational interaction, a momentum exchange occurs, causing the moons to swap while never approaching closer than about 10,000 kilometers. This dance happens about once every 4 years, and is the only known example of an orbital configuration like this present in the solar system. Number 1. Charon. When the New Horizons probe passed through the Pluto-Charon system, what was once thought to be a frozen, rather boring solar system backwater turned out to be one of the most exciting and dynamic sets of objects in the solar system. Pluto was a showstopper, and certainly worthy of the category of planet, showing all sorts of interesting geology, organics, atmospheric mysteries, and such, making it one of the most enigmatic objects in the solar system. But its moon Charon also proved to be full of surprises. Before its 1978 discovery in photographic plates by astronomer James Christie at the U.S. Naval Observatory, Charon was unknown, but it had oddly been predicted by sci-fi author Edmund Hamilton in his 1940 novel Calling Captain Future, where he described Pluto as having 3 moons. It actually has 5, but Charon particularly stands out. Charon and Pluto more accurately could be described as a double minor planet system, with Charon being about half the diameter of Pluto. One of the many oddities of this system is that the reddish patch that you see at the pole of Charon is actually part of Pluto's atmosphere. Yes, Pluto periodically has an atmosphere and transfers components of it to Charon's surface, but it's not just any material. It's organic tholins, molecules that may be related to life. One debate that's currently going on is how Charon formed. One idea is that it's a product of a glancing blow early in Pluto's history, much like our own moon is thought to be a product of such a collision. 2 objects hit and destroy each other and then reform into new bodies. The geology does not seem to bear this out, however, suggesting rather that Pluto and Charon have always been separate objects, but collided very gently at some point and came into an orbital equilibrium afterward. Also going on here is a rare case of mutual tidal locking. With Earth, the moon always presents the same face to us, but Earth does not present the same face to the moon. With Pluto and Charon, they always present the same face towards each other. Charon also seems to be geologically active, with cryogeysers and potentially even cryovolcanoes spraying out ice crystals and making fresh deposits on the surface. This may have led to a very strange type of feature on Charon. Described as a mountain in a moat, this feature, named Kubrick Mons after director Stanley Kubrick, is literally a mountain that's sitting in a depression. One idea is that this formed when a cryovolcano basically deflated the ground under it by depleting the reserves of ices underneath. But that explanation remains far from settled, sinking mountains, as it were. As data from New Horizons continues to be analyzed, even more mysteries of this strange moon may come to light. This list was just a sampling of the many moons that the solar system has to offer, and we very likely don't know about a significant portion of them yet. As we explore objects in the Kuiper Belt, some of which can be larger than Mercury or Pluto, or if Planet 9 is ever detected, which it may well have large moons of its own, then the list of strange moons of the solar system will grow. And there are other strange things lurking out there, such as the asteroid 10199 Chariklo, which does not have a known moon, but indeed is the only asteroid known to date to have its own ring system. Imagine what we will find as we continue to explore the solar system. Astronomy is always changing, and new ideas come to light each year, sometimes greatly expanding our understanding of the universe, and sometimes are just proven wrong. This is an ongoing process, it's science. So here are 10 recent, but somewhat odd, astronomical possibilities that are expanding our thinking on how we view the universe. Number 10. Expanding habitability. Not long ago, just a few decades really, life on other worlds was envisioned mostly as a surface phenomenon of planets. Worlds like Venus and Mars were actually assumed to be inhabited because, superficially at least, they appeared to be very similar to Earth to the instruments of the time. Venus being envisioned as a hot jungle world, and Mars as hosting a civilization building canals and plotting against humans. But as we learned the rules on how these worlds actually worked, typically through flybys of early space probes, we found that these worlds were nothing like what was envisioned, Venus being a hell world and Mars a cold desert. These did not seem to be likely abodes of life, but through the further study of those worlds, we have found that at one time, they are both believed to have had long periods where liquid water persisted on their surfaces, and the conditions, so far as we understand them, existed for life to have a genesis on either of those planets in addition to Earth. Fast forward to now, our understanding of how resilient Earth life is and how conditions of habitability still exist in diminished form on both Venus and Mars has led to a revival of the idea of both of those planets still hosting and possibly hinting of microbial life, Venus particularly with the recent detection of phosphine gas in its atmosphere. Life may yet hang on in the relatively clement upper atmosphere of Venus, and may be hinting through strange dark bands that appear in the Venusian atmosphere. On Mars, it's below the surface, where liquid water still exists, and with it the possibility of subsurface life that hints through phenomena like seasonal methane blooms, that while could be geologic in origin, might also be biological. But it doesn't end there. Also discovered have been a plethora of ice shell worlds, where oceans of liquid water are locked under ice that might provide an abode for microbial or even complex life. These places are many in number in the solar system, including Enceladus and Europa. But even the asteroid Sirius seems to host reservoirs of slushy liquid water, and with the same possibility of water found also at Pluto. Similarly, the Kuiper Belt objects are on the table for possibilities for life, despite being located very far from the Sun. But now the net is cast even further, with conjectural abodes for life now including the atmospheres of brown dwarfs and gas giant planets, and even rogue planets wandering without stars in the interstellar medium, and even the intergalactic medium, where liquid water in some circumstance could be sustained by geothermal heating through the radioactive decay of elements in the cores of those worlds. Even the universe itself was once warm enough for the entirety of it to have had a short-lived epoch of habitability, and while life may not have formed during that period, at least the conditions were there for a time, essentially everywhere. The point is, the more we think about habitability and just what that means, the more places seem to unlock in the universe for life, at least at some point in time. Perhaps some currently inhospitable appearing places, like planets around red dwarfs, or places that are not yet habitable, being more habitable than we might currently think. Number 9. How many habitable worlds can a star have? While our own solar system has had 3 nominally Earth-like planets as far as habitability, only one has remained so. There are complex reasons for why Mars and Venus did not remain habitable, but one question remains. Under ideal circumstances, how many Earth-like worlds can a star system have? The answer is 7. In a study by Stephen Kane and colleagues, link in the description below, they looked at the TRAPPIST-1 system, which is known to host 3 worlds within its habitable zone that might support liquid water. But even then, that system isn't ideal. So what happens when you have just the right type of star and just the right type of planetary dynamics, such as the lack of a gas giant to destabilize orbits? The orbital dynamics of a younger star system, known to have somewhat larger habitable zones, and the presence of a larger, hotter star could have up to 7. With a star like our own Sun, 6 planets with at least transient liquid water could be possible under exactly the right conditions. On the other hand, it has been said that Jupiter in our own system helped life on Earth by clearing out asteroids. It's unknown if a lack of a gas giant is a showstopper for life, but if not, then it could be the rule that rocky worlds like Earth are rather common, with multiple examples possible around sun-like stars. And there are also the ice shell possibilities like Europa, that greatly extend habitability in star systems, further raising the possibility of life, at least microbial, being very common in the universe. Number 8. The sudden instability of Betelgeuse. The prominent night sky star Betelgeuse is known for many distinctions, including being one of the few stars large enough and close enough to have its disk directly imaged, and for its prominent red color to be visible to the naked eye. Betelgeuse is also known for being a giant star nearing the supernova stage. This titanic explosion is expected to be soon in geologic terms, within about 100,000 years or possibly more. But in human terms, it's highly unlikely to occur within any given lifetime, but it will happen within someone's lifetime. Or is that really the case? Last year, Betelgeuse began to exhibit a period of very deep dimming, where the star became significantly fainter than normal by about 2/3. General variability with the star is normal, but such marked drops in brightness are unusual, leading some to speculate that it may be preparing to explode. The reason for the dimming was unknown, and a leading explanation at the time was that the star was simply being obscured by dust in the surrounding environment. And after that, the star seemed to recover to something close to normal brightness. That would have been the end of the story, but two things have very recently developed. One is that researchers found that the reason for the dimming was actually the star itself. Hot material was welling up from the interior of the star, cooling and forming dust grains, and then they were being expelled and blocking light. In other words, it's the star itself doing it, not the environment around it. The second thing is that the star wasn't visible from Earth for some months because of being behind the sun, so no one really knew what it was doing, though a reasonable assumption was that it was returning to normal. Now, the first space-based observations for the year are in, and it's back in the night sky, and it's still not normal. Betelgeuse's brightness is still varying. What this new drop in brightness means remains to be seen. Number 7. The sun may not have been alone. It is believed that about half of all sun-like stars in the Milky Way have companion stars forming binary star systems. Why the sun has no such companion has been an open question, and indeed there was a hypothesis decades ago that the sun might have a dim, difficult-to-detect red dwarf companion orbiting distantly, though this is now no longer thought to be plausible. So if the sun is alone as a star, was it always that way? Could the sun once have had a companion star and somehow lost it? In a paper by Avi Loeb and Amir Siraj, linked below, they detail that if the sun had an early binary companion of similar mass, it might explain the formation of the Oort cloud as we see it today, aspects of the formation of which have been difficult to model until now. This companion would have been present very early on when the sun was still within its birth cluster, and now would be long gone. At some point, the gravitational influence of another star in the cluster would have removed the companion, but left the material it helped to accumulate around the sun in the Oort cloud. But this also has implications for another odd hypothesis, that a ninth planet lies out there, and is affecting the orbits of objects in the outer solar system. If this is the case, then this binary star hypothesis might provide an origin for Planet 9, in that it was originally a planet orbiting the sun's former companion and was captured by our sun from it. Only further searching will prove or disprove the existence of this planet. As to whatever happened to the sun's companion, we'll likely never know, since it could literally be anywhere in the galaxy by now. But there is one oddity here. The star HD 186302 is so close to the sun in composition that it at least had to have formed in the same cluster as the sun. It's also nearly identical to the sun, only slightly larger, and seems to be exactly the same age. Other stars very similar chemically to the sun and almost certainly from the same stellar nursery have also been found, though none are as close as HD 186302. It's possible that this star is the sun's long-lost companion, or at least a close cousin. And given that the sun clearly has planets, including one with a civilization on it, it's not a far stretch to suspect that this might be the case for any other siblings of the sun from the same stellar nursery, since they would have had all the same available materials. Perhaps somewhere out there, the former twin of the sun also hosts planets and life. Number 6. Vanishing stars. Stars really don't like to just disappear. They tend to either violently explode and then leave some remnant, such as a white dwarf, black hole, or neutron star, along with a bunch of easily detectable dust and gas. Or they fade away like the sun will after its red giant stage to leave, well, a detectable white dwarf. Small stars like red dwarfs just persist and will continue to do so for trillions of years. What stars won't normally do is just simply go away. If they do, then it's reasonable to look at options beyond nature for an explanation, such as the activities of an alien civilization. Disappearing stars as a technosignature has been of recent interest within astronomy. If you can't think of an immediate natural way for something to happen, such as the disappearance of a star, then other options eventually come onto the table as you rule out natural causes. But it's important to remember that other things can dim or make a star disappear, such as a cloud of dust or gas obscuring it. And there are unusual natural options, such as the possibility of a star under certain conditions to collapse directly into a black hole without a corresponding supernova. But anomalies have been found, in fact, quite a few of them. The Vasco project, for example, has found at least 100 good examples and over 150,000 candidates of very red sources that appear to be stars or something like stars that simply disappeared or flat out appeared over a very short period of time in past sky surveys, on the order of decades rather than centuries. Whatever causes this is likely to be of astrophysical origin, though unusually so as far as we know, but something else may be at play. Only time and more research will tell. Number 5. Neutrinos do strange things. Neutrinos have always been rather odd things due to their ability to only weakly interact with anything else. For example, most of the huge amounts of neutrinos streaming off the sun that encounter Earth simply pass through the planet and go on their way as though nothing happened. But occasionally, an interaction does occur, which allows us to detect neutrinos, and the more we study them, the odder they seem. Studying neutrinos in astronomy is of great importance. An example of this would be in detecting supernovas. Since neutrinos are so non-interactive and travel at near the speed of light, they will actually be the first thing we can detect from a supernova, as photons will have been delayed in the interior of the supernova explosion. We will see neutrinos from a supernova before we actually see the visible explosion. But neutrinos also offer some head-scratching mysteries. One of these involves Antarctica. Researchers working on that continent have in recent years detected neutrinos seemingly not coming from the sun, or anywhere for that matter. Further, they are traveling upwards from the ground rather than coming in from space. Where exactly these neutrinos are coming from is unknown, but more recent analysis has shown that they might actually not be neutrinos at all, but rather reflections of ultra-high energy cosmic rays striking compacted layers inside the glaciers beneath. We shall see. Number 4. The kilonova and gravitational waves. Gravitational wave astronomy was once thought by some to be out of reach. Experiments to pick up gravitational waves directly went without definitive results for years, but there were indirect hints that they existed. That was until 2015, when the first direct evidence of gravitational waves was detected. One cause of the gravitational waves that we can detect right now is the merger of two neutron stars, or a neutron star and a black hole, in a phenomenon known as a kilonova. In addition to sending out ripples in space-time, these titanic mergers also have another interesting effect. They produce gold, a lot of it. The debris formed during these mergers is rich in heavy metals like gold and platinum, giving one mechanism for how these metals are made in the universe, and in fact may be the origin for the gold and some of the other heavy metals here on Earth. But lurking out there in the galaxy are truly enormous amounts of precious metals, beyond far more than what we can ever find on our planet. Number 3. The closer you look, the stranger it can be. As our ability to study astronomy has improved with new, more precise equipment, the universe has been brought into unprecedented detail. Of course, with this new level of scrutiny is bound to come more mysteries, and few recent discoveries are more mysterious than the star HD 139139. This star at first glance appears rather familiar. The main component is a G-type star, very much like the Sun. There's also a companion star, believed to be a Type K star. The Kepler data showed dips in the starlight from the system that for all intents and purposes look like exoplanets transiting one of the two stars, though it's still unclear which. And the dips kept coming, with 28 observed over several months. But the dips did not appear periodic, meaning they didn't seem to be the same planets passing by over and over, and other aspects of the light curves looked weird. Save for one transit, which was larger, all of the others looked like apparent planets, all just about the same size. That's weird. Potential explanations include a planet disintegrating, asteroids impacting each other, and even just sunspots on one of the two stars that don't last long. And it's very likely something like that causing it. But if you were an alien civilization that wanted to produce some kind of signal and produce something that looked unnatural in order to announce their presence to the galaxy, they might do something like this. Create something so unnatural looking that anyone seeing it would have to conclude that it wasn't natural. That idea was advanced by astronomer Luke Arnold, that if you produce an unnatural looking signal in a light curve, such as a louver or unnatural shape passing in front of a star, other scientists in the galaxy might see that and know that a civilization was there. That's not likely the case with HD 139139. It's very likely some odd astrophysical phenomenon that we simply haven't seen yet. But there's something else here. This star is one of just 0.5% of stars in the galaxy that can actually see Earth transit the Sun if they had a photometer like the Kepler spacecraft. Just barely, but they could see us. But as we expand into space and build huge structures of our own, such as Dyson swarms and O'Neill cylinders, our star system might just begin to look very strange to some alien astronomers somewhere nearby in the Milky Way, and they will conclude that there must be a civilization here. Number 2. Our own world may hold the key to life in the universe. We've always mainly thought to look outward for evidence of alien life. This is only natural. It's much easier to prove that a radio signal from light years away is of truly alien origin than anything you might find locally. But there is an option within science to look for microbial life here on Earth that either had a separate genesis from our kind of life on Earth or originated from somewhere else. Known as the shadow biosphere, the possibility of the presence of separate abiogenesis or even a seeding of alien life on Earth through panspermia is a tricky subject, as this kind of microbial life might actually be very difficult to detect using the equipment we have. But there is one possibility, the phenomenon known as desert varnish. This is a thin, layered yellow to black varnish that appears on exposed rock in very dry environments on Earth. The composition is mostly clay, which doesn't scream life, along with oxides of iron and manganese. Manganese is strange since it's fairly rare in the Earth's crust, and desert varnish seems to contain a lot of it, opening up the possibility for manganese concentrating microbes. And there's also the presence of organic matter within desert varnish. More recent studies have suggested that biochemistry isn't necessarily needed to form desert varnish. But oddly enough, desert varnish also seems to be an excellent environment for fossilizing microbes. This is important, since a recent discovery of what at least appears to be desert varnish on rocks on the surface of Mars suggests at least that there may be an easy surface method for searching for evidence of fossilized microbes on Mars. But if a true alien shadow biosphere is ever found here on Earth, or for that matter on other bodies in the solar system, it will tell us that life is likely very common in the universe. How often that life becomes a civilization remains to be seen. Number 1. We are far from isolated. In a way, in the history of science, we have always had a kind of separation against our inclusion in the universe at large. We saw the heavens, and then we saw the Earth, and generally we felt that we were either special or some backwater separate from the rest of everything else. This started to change when it became clear from the work of Gene Shoemaker that we are not separate from the solar system, but rather still subject to bombardment from comets and asteroids. And in the vast history of the Earth, we were much more subject to it in the past, as the surface of bodies like the Moon show. But that's still the solar system. What of the rest of the Milky Way? Well, as Oumuamua, the first confirmed interstellar object passing through the solar system, followed by the interstellar comet Borisov, we find that we are not in any way protected or isolated from the rest of the Milky Way either. This has led to a flurry of new thinking about what else might be passing through the solar system. Amir Siraj and Avi Loeb have pointed out in several recent papers linked below that we are not as isolated as we think. There may be evidence of subrelativistic particles shot out into space by nearby supernova that may have left tracks in lunar geology that we could study, or even interstellar meteoroids that can be tracked to have entered Earth's atmosphere. It's even possible that interstellar meteorites might land on Earth and survive for study. though we already have evidence of interstellar dust grains and very primitive meteorites that have been found on Earth, and even from probes we've sent into space. The bottom line here is that we are not isolated and are very much a part of the life of the Milky Way galaxy and always have been, opening up the way for science in the not-so-distant future to study the environments of other star systems from the comfort of home. What might they find in comparison that is different out there to what we have here? It's an open question. One of the more remarkable developments here on Earth in astrobiology is the sheer number of new ways that have been recently thought of in how and where we might look for both biosignatures of life itself, but also technosignatures of alien civilizations. So here are 10 interesting recent developments in astrobiology that might further our search for other life in the universe. Number 10. Enceladus methane. Of all the ice shell moons in the solar system that could in principle support life, Europa and Saturn's moon Enceladus stand apart, both because their subsurface oceans are within the realm of accessibility and investigation, but also because both of these moons bear hints that there may be life in their oceans. Enceladus took a step forward recently on this count. A few years ago, the plumes of water ice streaming from fissures in the moon's ice shell were found to contain all the nutrients needed for life, and indeed some indication of geologic processes such as geothermal vents on Enceladus's ocean floor. While not proven to exist, only hinted at, such vents could serve as ready energy sources for life, such as oceanic vents do here on Earth. But there has been another recent development. The plumes streaming from Enceladus and indeed Europa give scientists direct access to water originating from the oceans of those moons. That can be studied remotely, and indeed directly. This happened with the Cassini spacecraft, and it discovered a strong signature of methane in the plumes of Enceladus. This is important, given that methane is a biologically produced gas, though unfortunately there are other natural non-living processes that can make it as well. But recently a team of French and American scientists constructed mathematical models to try to determine what was producing the methane at Enceladus. The models predict that it's either life, consistent with methanogenic microbes around geothermal vents here on Earth, or some unknown methane-producing natural process that isn't anything like what happens here on Earth, giving us a tantalizing hint, perhaps the strongest yet, that Enceladus may have life. Number 9. 1,700 star systems can see us. When pondering the search for extraterrestrial intelligence, the natural thing to ask is, since we're looking for intelligent alien civilizations, are they likewise looking for us? This is a hard question to ponder because there is the possibility that the answer is no. There may be alien civilizations that concluded that intelligent life is so rare that they don't even bother to look, in which case they may never know we're here and don't care if we are. But it's also equally possible, perhaps even more likely, that they are curious and do look. After all, if they've built a civilization based on science and engineering, then some natural curiosity must be at play. So the question becomes, how easy is it to spot us? Well, there are multiple ways it could happen, so long as the alien civilization is close enough to detect us. Further than about 100 light years out, they would see Earth as it was 100 years ago. And going much further back than that, we become undetectable, even though we were already well on our way in developing our civilization here on Earth. But that's because of when our detectable technologies, such as radio, saw their advent. But Earth is obviously much older, and we detect exoplanets, habitable or otherwise, using the transit method, so long as the exoplanets we're looking at happen to line up to the observer to create a transit signature. So how many other known exoplanets can see Earth transit the Sun? This was looked into by Lisa Kaltneger and colleagues, because vantage points change over the last 5,000 years. In our local neighborhood of about 325 light years out, roughly 1,700 star systems have been in a position to actually spot Earth transiting the Sun, within a total of about 335,000 stars in the Gaia spacecraft data, with about 1,402 still being able to currently spot our world, and 75 of these are close enough to have spotted our radio signals. And transiting exoplanets are excellent candidates to try to characterize and study exoplanet atmospheres as our instrumentation gets increasingly better in the future. If someone out there has done this with a transiting Earth, they would have seen fairly clear evidence of Earth's biosignatures, and may have long suspected that something interesting was going on here. Whether that has in fact happened, and this planet is being watched by an alien civilization from afar, is an open question. Number 8. Artifacts on the Moon. So far, the major way in which SETI has been conducted is through the search for radio signals emanating from alien civilizations. This makes sense to a degree because our own civilization produces all manner of radio signals and they escape into space. But the problem is that they are on the whole very weak as far as interstellar distances go, and only a few times in the past have we sent out truly powerful signals that could be picked up by SETI experiments across the galaxy. One was unintentional in the form of using radar to map asteroids, and the other a signal intended for alien civilizations to see, both sent by the now destroyed Arecibo radio telescope. But all were one-offs, and if the alien scientific bar is the same as ours, they would simply be WOW signals that were only detected once and prove nothing. To go beyond that would be to construct what the original investigators in SETI expected might be found, a giant directional or omnidirectional beacon that could be seen across the entire Milky Way. This has not been found, and there may be a good reason for that. It's simply not worth it to build such a beacon and invest titanic amounts of energy into it, and then long term, as in running it for thousands of years, in hopes that someone else might see it. It's still possible that such a thing might exist, but it's sort of a long shot. This has led to thinking in SETI that there may be far cheaper ways for civilizations to make contact with each other, some of the magnitude of 1 trillion times less expensive. One way here is the Benford Lurker. The idea here is that an alien civilization might send an artifact at sublight speed, perhaps from a passing star system, and then deposit such artifacts in promising star systems that have habitable exoplanets. In our case, Earth being a very obvious one that's been sitting here for 4.5 billion years. These artifacts may be active and turn on and begin transmitting at some point, or may be passive, like time capsules preserving information and artifacts about the civilization that left them, which could possibly be extinct by the time their artifacts are found, constituting not a technosignature, but a necrosignature. Obvious places to look for such artifacts might include collection points where Jupiter's gravity might cause interstellar objects to congregate that it captures, or co-orbital objects with Earth, or even the surface of the Moon or buried beneath it, where such artifacts might last for billions of years, waiting to be discovered by humans. Number 7. Super-rotating oceans. One of the biggest hits to the possibility of life in the universe in recent years has been seemingly ever-lowering chances of life developing on exoplanets within the habitable zones of red dwarf stars. Among the many problems that have been realized about the most abundant class of star in the universe is that early in their lives they tend to be volatile flare stars. The other problem has been tidal locking, where exoplanets within the habitable zone of these tiny stars are so close in that they tidally lock, showing only one face towards their stars. Much like the Moon is tidally locked to Earth and only shows one side to us. This problem of tidal locking has created problems for envisioning how life might evolve on these worlds. Specifically, in that conventional wisdom would suggest that one side of the planet is always getting baked and the other frozen, leaving at best a temperate twilight zone at the edges of light and dark that might allow for a chance. But that has recently been called into question, and oceans and life around these worlds may be aided by a different factor: super-rotating oceans. We clearly live on a planet that can transfer heat around. It's tilted and rotates and is unevenly heated. Yet ocean currents, the atmosphere, etc. move heat around. So why couldn't this happen on a tidally locked world? It could, but it must do it faster than the tidally locked planet rotates, meaning that the ocean currents on those worlds must super-rotate to move heat to the cool side and expand the exoplanet's habitability. But Venus and several other bodies in the solar system, and occasionally even Earth, show us that this is possible with atmospheric superrotation. But on a tidally locked exoplanet orbiting a red dwarf, you're going to need the ocean currents doing it. Recent modeling has shown this is actually quite possible if you get the right winds and conditions. And you might have super-rotating oceanic currents on these kinds of exoplanets, broadening the way for life to arise on those worlds. but it's also situational. For example, if the continents on the exoplanets are arranged in a bad way, should continents be common things in the universe, which they very likely are, they could alter or stop those currents entirely. So however it might work, it's going to be very different for every exoplanet. Number 6. The Alpha Centauri A exoplanet. The nearest star system to us, the Alpha Centauri system, has been the focus of recent research regarding a roughly Earth-sized planet within the habitable zone of one member of the system, the closest one, Proxima Centauri. This exoplanet, Proxima b, takes the record as the closest known to us. But there have also been suspicions that the two other members of the Alpha Centauri system may also host worlds, and both of those stars are not red dwarfs and do not suffer from the problems associated with red dwarf exoplanets and life. It's made up of a Class G star like the Sun and a Class K orange dwarf. Now, it appears that the Type G member of the system has a planet within its habitable zone, though a planet very different from Earth. It appears, at least initially, to be about the size of Neptune, and the planet is still unconfirmed, being discovered as a heat signature by the European Southern Observatory's NEAR project. But given the proximity of the Alpha Centauri system, this planet, along with Proxima b and another candidate further out from the red dwarf, will no doubt be among the best candidates we have for at least characterizing the atmospheres of other worlds. Number 5. The BLC-1 radio signal. Last year, a signal was detected by the Breakthrough Listen project that was rather unusual for a SETI signal, in that it made it past all the filters in place at the time and took its place as the first candidate signal of that project, hence Breakthrough Listen Candidate 1. The signal was needle thin, which is what you would expect from any technological alien signal or interference from Earth, and seemed to emanate from the direction of the Proxima Centauri system, the closest one to Earth, though this was only a general direction rather than a direct detection from that system. It was also suspected from the start that the signal was some kind of interference from Earth, especially since it was picked up near a very arbitrary human frequency number based on Hertz, which is our own 60-second intervals aliens would know nothing about. It was only odd that it made it past so many filters designed to eliminate such interference. The signal was later shown to convincingly be a matter of Earth interference, and signals like it were spotted at different frequencies but with similar characteristics. The exact source, to my knowledge, isn't yet known, but this one has left the stage as a candidate for an alien signal. But it's still useful in that it shows yet another type of interference that can create a false positive in SETI that is really of earthly origin. This allows for further filtering to be designed to catch this type of interference as a known earthly signal. One of these days, however, a signal may come through that passes the filters but cannot be attributed to Earth interference, but rather, more likely, a signal from an alien civilization. Number 4. The origins of RNA. One of the biggest questions within the science of figuring out the origins of life, what sequence of events happened to produce RNA, which is thought to have happened before the advent of DNA, and in fact may have been involved in the creation of the latter. But the origin of RNA is obscured, and is thought to have been related to something that happened in an abiotic chemical process. What exactly that is remains a mystery, but we might now know more. The Miller-Urey experiments and successors have shown that biologically related molecules can arise from non-biological chemical processes, but there's always been an open question of whether they might have been a missing link, some abiotically produced precursor to RNA that led to RNA itself. Recently, some hints at a chemical pathway were found by researchers at the Georgia Institute of Technology that get closer to looking like RNA and ordered genetic information, rather than the chaos of some very complicated chemistry. Cracking the nut of just how RNA and ultimately DNA came into existence is going to be of the utmost importance to astrobiology, and it's something that can be done here on Earth in the laboratory. We may well know the answer to these questions in coming years or decades, and we will be able to not only say that the process is either straightforward and probably happens all over the universe, or is very rare and difficult and a matter more of chance that may not be common at all, but also give us clues on what specific conditions are present on exoplanets that might make them good candidates for life to exist, or even eventually arise. Number 3. Superhabitable candidates. One of the more interesting ideas that has come up in our exploration of exoplanets is the idea that Earth may not actually be the ideal world for life to exist, and that there may be planets out there better than Earth. There are multiple ways that this can be envisioned. For example, what of a better star? Our Sun is really mischaracterized. We have tended to see it as a moderately long-lived Type G yellow dwarf. Well, here's the thing. It's not yellow and it's not a dwarf. It's rather large for a star in comparison to most other stars. It's more like a white giant, and is increasing in luminosity as it ages, meaning that its ability to support life on Earth will end much sooner than its red giant phase. It will bake this planet in about 600 million years, and that will be it for life as we know it. It will become a microbial planet once again for a while, but even then that comes to an end at the hands of the increasingly luminous sun. In short, we're stuck next to a monster that had a long enough quiet phase for life and a civilization to arise, but not for long. If indeed the aliens of the galaxy work on much longer timescales than we do, our first SETI message may be from a frantic galactic community offering to send bottled water and hold a million-year-long bake sale to fund our evacuation to a better star. And then there is Earth. It's actually pretty easy to imagine a planet better than Earth, but also not that dissimilar. One can imagine slightly larger worlds, as far as surface area, that can have more landmass distributed over a greater number of smaller continents. The interiors of continents and past supercontinents on Earth tend to be deserts, so what of a bunch of smaller ones with better access to water? Or a larger planet, with a longer-lived molten core, making for better magnetic fields? Or how about different oceans? Earth's oceans get less habitable the deeper they get, yet life abounds in shallow waters, so what of a planet with shallower oceans? How about a planet around a long-lived orange dwarf that's older than Earth, and had a much longer stable period for life to evolve and thrive? How about temperatures? Is it possible to have a better temperature mix on a planet than Earth has? The list goes on. So have we ever found any candidates for superhabitability? The answer is yes. There are actually 24 recently identified candidates. They're all sort of ambiguous. We really are still in the infancy of characterizing exoplanets, but a few stand out. One is KOI 57515.01, which is a super-Earth, but not one so huge as to probably not be habitable. It's older than Earth by 1 billion years, and enjoys an orange dwarf as its host star. This would lead to comfortable surface temperatures, but a bit cold. However, we don't know anything about its atmosphere, so that may allow for warmer temperatures, and thus superhabitability. Another is KOI 5554.01, which is like a much older Earth, similarly sized, around another yellow dwarf. Though maybe that's not such a good option, even though it seems to support comfortable temperatures. As more study continues and more candidates come to light, this idea of superhabitability may become one of the hottest issues in astrobiology, especially if biosignatures are found associated with one. Number 2. SETI and FAST. One of the more important developments within radio astronomy in recent years has been China's development and construction of their 500-meter FAST radio telescope. This enormous telescope promises to provide a significant increase in global radio telescope capability for science. But there's always been the question of what China might do with it in regards to SETI. This plan is forming up and seems to constitute a solid effort in the field. So FAST, too, will join the search for extraterrestrial intelligence. But as we've seen with space exploration, and indeed the geopolitical ramifications of that, along with nation-state rivalry, the question is how this would affect any effort in being the first country to find an alien signal. Who makes the discovery first? Because of the nature of SETI, this is going to be difficult, because it almost has to be a global team effort. If a signal is picked up, geographical location becomes key in confirming it, because to do that requires radio telescopes across the globe to very quickly turn their attention to such a signal before it disappears. And if it's only seen once, it may be interesting, but it doesn't answer any questions. This leaves certain targeted searches that can be searched for again by the same telescope that might be kept secret for a time, but even then, confirmation of such a signal is going to be needed. But as with anything regarding SETI, the more the merrier. and it's a good thing that VAST is going to look into answering one of the greatest questions we humans have. Are we alone? Number 1. Hydrogen worlds. A huge question about just where life might exist and arise in the universe involves biases and certain realities. One of these is just what we consider a habitable atmosphere, in which we tend to look at our own atmospheric mix. But Earth's atmosphere was not always like this, and indeed, early on when life first appeared, it was radically different and did not contain the oxygen levels it has now. That was a result of life. So what other sorts of exoplanet atmospheres might also host life? One is pure hydrogen. Researchers recently experimented with E. coli and various species of yeast to see if they could survive in a hydrogen atmosphere. They didn't do as well and grew more slowly, but survive and reproduce they did. This opens the way for rocky planets with hydrogen-rich atmospheres to be on the list of candidates for life, and even certain biosignatures, even though they aren't particularly Earth-like in their atmospheric makeup. We live in a rather nice galaxy. From a dark location, you can see it stretching across the night sky. From a distance outside it, it's thought you'd see it as a grand barred spiral galaxy. It also has a rather large galactic habitable zone. Essentially, if you're not near the radiation environment of its center or various star clusters, and not out at the edges where there isn't that much material, your planet has a fair chance to develop life if you have the right basic elements available to you. We live near one of the spiral arms of the galaxy, something of a calm backwater, and our planet clearly has life. There may well be others. But the Milky Way can be a tumultuous place, where entire star systems can get tossed out at high speed under the right circumstances. All galaxies should be like this, meaning that there is a population of stars, likely an enormous amount, along with their planetary systems, that wander intergalactic space indefinitely. These would be extraordinarily difficult to find, unfortunately, needles in something far bigger than a haystack. But there are instances of planets detected in other galaxies beyond our own, usually by chance. These collectively are termed extragalactic planets, in the sense that they are not in the Milky Way, but may be located within other galaxies or beyond their own. These fall into two categories. The first is a planet or system of planets bound to a star, like our solar system. The second are wandering rogue planets with no star that wander space on their own. No extragalactic planet has thus far been directly discovered. There's a reason for this. It's extremely difficult to detect planets at such extreme distances, even within our own galaxy. For example, the current most distant planets known in the Milky Way come in at about 27,000 light-years from the Sun. That's a long way, but it's still less than a quarter of the size of the entire galaxy. While there are very likely many more planets further out in this galaxy, we have yet to be able to detect them with the equipment we have. And indeed, we may never know about a majority of the planets present in the Milky Way, due to both distance and the sheer numbers of them that must be out there. And we have only a handful of methods right now to detect the presence of planets around other stars. It's even more difficult for extragalactic planets, but there's no reason they shouldn't exist and indeed be common. And while there are no directly observed examples, there are some indirectly discovered candidates. In 1996, observations were being made of a quasar being gravitationally microlensed by another foreground galaxy. In the foreground galaxy, an anomaly was seen that is believed to be due to the passing of a roughly 3 Earth-mass planet. This fluke event, which can't ever be confirmed, may have given us a glimpse of a planet an astonishing 4 billion light-years away, at a time when the very first exoplanets in our own galaxy were just being discovered. A more recent discovery involving microlensing is an exoplanet discovered in the Andromeda galaxy that's thought to be a very large gas giant, bigger than Jupiter. A planet was also detected around an X-ray source in the Whirlpool galaxy. This system is thought to either be a neutron star or a black hole, accompanied by a supergiant star with a planet eclipsing the X-ray source. Certainly not a good environment for life, but a planet in another galaxy nonetheless. Perhaps the most interesting indirect detection of extragalactic planets came during another microlensing event, this of the quasar RX J1131-1231. In the foreground galaxy doing the lensing, evidence was found for a large group of rogue planets not bound to any stars. The masses of these rogue planets seem to range from the size of our moon to roughly the size of Jupiter. These planets are wandering their galaxy aimlessly, some for untold amounts of time, and others may get ejected from that galaxy to wander intergalactic space. But even in intergalactic space, life remains an option. While life requires certain criteria, such as liquid as a solvent, not necessarily but most likely water, along with nutrients and an energy source, this is all still possible with intergalactic exoplanets not bound to stars. There are two ways to provide the energy source to keep life going and liquid water liquid. One is obviously geothermal heating. This would be things like geothermal vents here on Earth, and even underwater volcanism to keep the temperature of the rogue planet up. Another option is the presence of a huge gas giant planet, with life existing at one of its moons in a similar way to how Jupiter's gravity flexes Europa to provide heating to maintain a huge ocean underneath a shell of ice. This too is possible between the galaxies, but good luck finding any of these kinds of planets given the distances. We may never detect any of these or any potential life on them. But where it gets much more difficult is the question of civilizations. Here you probably need the presence of a star for this to occur, or at least be detectable. Unbound intergalactic or extragalactic exoplanets would be very limited on energy sources despite them being present. They might have geothermal or gravitational flexing, but this would place very severe limitations on both the development of complex life itself and even more limitations on intelligence and a civilization. If by some chance intelligence did arise, it would be a locked-in intelligence. This seems to be a rather sad scenario. They probably wouldn't even have astrophysics, since all they'd see by looking up is a wall of ice. They might conclude that's all there is, though they might also suspect that there's more due to the presence of fissures and water leaving their environment. Perhaps somewhere out there is a debate raging under an ice shell about what lies beyond the ice. I'd imagine they'd be in for quite a surprise when they found out about the barely fathomable vastness of intergalactic space. They might wonder if they are alone, but for all intents and purposes, they may as well be. But the odd thing here is that such an alien world might seem more familiar to us than us to them. They would not have dry land, at least in the same way we do, and thus may not have even conceived of creatures that can walk around in an atmosphere rather than a liquid. But in our case, we have both an atmospheric and oceanic environment on this planet, and that might lend us some insight on imagining what life might look like beneath an ice shell. They would possess some type of aquatic physiology, which is extremely varied on our planet, but perhaps they might not be unlike that of Earth due to convergent evolution. Convergent evolution is an interesting topic in itself, since it may provide us with one of the few means we have to imagine what an alien species might vaguely look like. Our planet is home to a truly bewildering array of bioforms. A parakeet doesn't look much like a hippopotamus, yet both are complex life present on this world. But sometimes things converge between species simply because a good design is a good design. An example here would be dolphins and sharks. They have similar lines and fins, yet are only very distantly related to the point that it wasn't relation that created that convergent physiology. It was the aquatic conditions of their evolution. This may be true for any aquatic civilization that they might look something like fish, though just as easily they might look like jellyfish or cephalopods. But at least it's an idea, albeit very general. The problem is that aquatic, complex life doesn't usually lend itself to making and using tools, though there are exceptions, the octopus being one. But otherwise, it's difficult to manufacture something with aquatic physiology. Even harder would be mastering the smelting of metals underwater, since fire is a problem, though there is the volcanism. In any case, the ice shell worlds one might find in the universe do not seem good candidates for civilizations. Intelligence maybe, but beyond that, not so much. But there are scenarios that can be imagined where an advanced civilization might still exist and be detectable in the space between the galaxies, though it seems unlikely anyone would just happen to be pointing a radio telescope at just the right place to ever pick them up. These would include civilizations that developed around ejected stars. It's less likely for a pre-existent civilization to get ejected due to it usually being a phenomenon of younger star systems, or very hostile conditions like a pair of black holes, though it can also happen during galactic mergers. More likely are civilizations that formed in the intergalactic medium after ejection, or left intentionally. These would be lonely civilizations indeed, separated from other wandering star systems from distances in general far greater than what would be found in a galactic environment. These would be civilizations more or less limited to the resources of their own star system, which might compel them to try to artificially join a galaxy eventually, through the use of a Shkadov thruster megastructure, essentially half a Dyson sphere, to propel their star towards a galaxy and eventual capture. This would become increasingly essential for a civilization as the universe ages, due to raw materials growing scarcer and scarcer within their own system. On the other hand, such a remote location might favor a civilization if they've converted themselves into a machine civilization. Here they might take advantage of the very low temperatures present in the intergalactic medium for more efficient computation, though it's hard to envision them not also eventually going in search of more raw materials. In the end, though, this would be a hard existence for any civilization, and perhaps an unlikely one. It may be that the overwhelming rule of civilizations is that they are confined to galaxies, and perhaps are too rare to appear in the intergalactic medium very often, if ever, but at least it's food for the imagination. And as resources in the universe grow scarce and the stars begin to burn out, perhaps the last civilizations, for all intents and purposes, will all be intergalactic. One of the most striking things about the solar system is that there are huge differences between the atmospheres of each of the planets. And it's not just fundamental differences, such as the atmosphere of Jupiter when compared to Earth, but also with the terrestrial planets as well. For example, as far as percentages go rather than actual amounts of gas, did you know that Earth is actually not the most oxygen-rich planetary atmosphere in the inner solar system? That distinction actually belongs to Mercury. While Mercury's atmosphere is tenuous at best, barely existent really, it is made up of 42% oxygen, and it has an unusually large amount of helium, 8% due to its proximity to the Sun, and it's got 22% sodium, odd planet indeed, and not really very much like anything else in the solar system. But remember, that atmosphere is more of a trace than a real atmosphere. Then there are Venus and Mars. These are carbon dioxide planets. Venus is at 96% carbon dioxide and Mars at 95%. But they are at very different pressures, Venus very high, crushingly so, and Mars very low. This is in drastic contrast to Earth, which has very low amounts of carbon dioxide, but a massive amount of nitrogen and oxygen. Mars and Venus have some nitrogen as well, 4 and 2.7% respectively. But why does Earth have so much nitrogen? Well, this comes down to some specific features of nitrogen and its compounds. It's a volatile in most of its forms, so it likes being a gas at low temperature. It also doesn't really like to react with the materials that make up the Earth's surface, meaning that it doesn't get locked up in geology like highly reactive oxygen does, and also carbon dioxide. The last thing that favors it is that it doesn't get broken up by the sun's radiation here on Earth. But interestingly, nitrogen isn't completely useless, and it's a major thing in agriculture to fix nitrogen in the soil as fertilizer. But in some cases, nature has already figured out how to do this. Outside of astronomy, one of my big interests is gardening. And there actually are plants that can take atmospheric nitrogen and fertilize itself by way of a billions-of-year-old symbiotic relationship with bacteria that can work with nitrogen. Sometimes the bacteria is literally present in the seed itself, so it can colonize the soil around the plant and then both of them thrive. One example of this is the green bean, or indeed all members of the faceless family. One wonders what possibilities symbiotic relationships offer between different forms of life on an exoplanet. But why doesn't Mars or Venus also have much more significant amounts of nitrogen? Well, Venus has plenty of nitrogen, actually more than Earth. It's just that the atmosphere is far denser, and it has a lot more carbon dioxide. The reason for this is because Earth can essentially process CO2 through the carbon cycle, subduct it under the surface of the planet, lock it up in oceans, and, well, life, and so on. Venus doesn't have any of this, so the atmosphere on that planet is where all the carbon goes. Nitrogen on Mars is a different story. Here the nitrogen is missing, assuming that Mars got a supply of the element like Earth and Venus did. One way Mars can lose nitrogen is loss into space, and it lost most of its original atmosphere. The other way is chemical. Nitrogen can get locked into nitrates in the Martian soil, as well as other processes. Essentially, the chemistry and the atmospheric loss robbed Mars of most of its nitrogen long ago. The differences between the terrestrial planets in the solar system show how different atmospheric circumstances can be in star systems between member planets. No doubt we'll find much more variation in exoplanets when our instrumentation allows more thorough characterization of exoplanet atmospheres, particularly the long-awaited James Webb Space Telescope. It will be interesting also to not only look for analogs of Earth, but also exoplanets similar to Venus and Mars. That's assuming that star systems similar to ours are common. But what if they're not? There are actually some early indications that our solar system actually isn't the norm. It actually may end up being very rare as a configuration, and bear implications on the possibility of life and eventually civilizations. And that's a bit spooky, but also a potential solution to the Fermi paradox, that star systems where life can develop are exceedingly rare, thus explaining the Great Silence. But the assumption within science has always been that Earth should be nothing special, and that we occupy no particularly special location in the universe. And that thinking has served science well. As late as the 1990s, the existence of exoplanets had not been confirmed. But by then, almost all astronomers were of the opinion that there was simply no reason why planets should be rare. As it turns out, they're not. We now know of several thousand exoplanets, and the tally grows each year. But so far, nothing quite like the solar system has been identified. In fact, it seems to be the opposite, where multiple planet systems tend toward a pattern of similar-sized worlds at regular spacing. Our solar system generally obeys the spacing part, at least the inner solar system, but not the regular planetary sizes. It may once have to a degree, but the violent impacts and the factors that shaped our solar system may have been different from that of other exoplanet systems. Why this system would be different and how rare it actually is remains to be seen. But the study of the atmospheres of terrestrial exoplanets also promises another possibility, that of technosignatures such as CFCs and nitrogen dioxide that might point to an industrial civilization present on that planet, or strange oxygen and methane levels that might indicate life, such as the biosignature that Earth itself has broadcasted to the rest of the galaxy's scientists for billions of years. But what of types of terrestrial exoplanet atmospheres for which we have no example in our own solar system? While the study of exoplanet atmospheres is in its infancy, we should gain new insights into them with coming instruments like the James Webb Space Telescope. Still, some work has been done in exoplanet atmospheres, particularly giant planets. But with terrestrial small worlds like Earth, not a great deal is yet known, but there has been some modeling. But the problem here is that planetary atmospheres evolve. Earth, for example, once had significant hydrogen in its atmosphere. It no longer does, in part because Earth simply can't hold on to hydrogen. But other types of stars, such as M-type dwarf stars, may be capable of dramatically altering or blowing away entirely an exoplanet's atmosphere, in which case it might actually form a second atmosphere entirely. And there is a suspect for this. The planet is designated GJ1132b, and it orbits a red dwarf. It's cool enough for an atmosphere and is only about 40 light-years from Earth, which makes it easier to study. It's about 20% larger than Earth, but is suspected to be terrestrial in nature. But it's hot, receiving 19 times more solar energy than Earth does due to close proximity to its parent star, and it's very probably tidally locked. Earth analog, this is not. This is also an unusual planet in that it probably doesn't have much topography, rather a relatively smooth surface with a thin crust, then becoming fully molten not far below. And it has an atmosphere, but it's nothing like ours, consisting of hydrogen, methane, and hydrogen cyanide. Think of a probably hazy, hotter than Venus hellscape, dotted with exposures of molten lava and burnt solid crust, not unlike freshly solidified lava here on Earth. But this planet probably should have no atmosphere at all. The red dwarf it orbits should have stripped off any atmosphere it had early on, meaning that this may actually be the planet's second atmosphere, generated by geologic processes going on within it. It may have originally started as a planet with a large, gaseous atmosphere. Essentially, it's the core of a sub-Neptune. But more recent work has cast doubt on this detection. It may have no atmosphere after all, which underscores that we really are just beginning the study of exoplanet atmospheres. And there are many other possibilities. What of a world so hot that it has clouds of vaporized rock? or hot Jupiters so hot and so close to their stars that water itself breaks down, leaving them with very dry atmospheres, whereas planets just a little cooler typically have water vapor. Or how about an oxygen-rich world where the oxygen is not being produced by life as it is here, but by geophysical processes? And it's worth noting that given the study of other atmospheres outside of the solar system is fairly new, especially with terrestrial worlds, the actual nuances of these atmospheres isn't yet known. It's extremely difficult to model Earth's atmosphere, for example, and we have no shortage of data on it. Modeling an exoplanet accurately will be limited to the basics of these worlds, at least until someone goes and visits them. But what of our own atmosphere? Being essentially the holy grail of terrestrial worlds, what will become of Earth's atmosphere? There are several possibilities. If left to its own devices, the atmosphere of Earth will suffer at the hands of the Sun. As the Sun's luminosity increases as it ages, Earth will become a place where surface life is no longer possible, and the oceans will simply evaporate, blanketing the world in water vapor, itself a greenhouse gas, creating what's known as a moist greenhouse planet. And then it runs away with itself as the greenhouse effect grows increasingly worse, until eventually the surface of the Earth melts, which if it hadn't happened already, all life on this planet will cease. And the planet itself will probably end with being engulfed by another type of atmosphere entirely, that of the Sun as it swells into its red giant phase. Or maybe not. Earth's atmospheric clemency could be extended in principle through terraforming our own world. There are things we can do, if we're still around, to stave off, at least for a time, the effects of the brightening sun. One simple method of doing this is a star shade, where a small, but over time increasing percentage of the sun's light is blocked out from a shade in space, thus mitigating the effects of the aging sun. And there are other changes to other planets in this regard as well. Both Venus and Mars are in principle terraformable, and by that time might be viable inhabited terraformed worlds. We certainly have the time to do that on the order of hundreds of millions of years into the human future. And while all of this happens, the sun's natural habitable zone moves outward, opening up possibilities to terraform and settle moons further out in the solar system. And moons can hold their own atmospheres, even substantially, as Titan shows. So who knows what the future of planetary atmospheres in our solar system is going to be like? At first glance, supernovas would seem to be very straightforward affairs. Giant, short-lived stars go out in a blaze of glory and explode on a titanic scale, leaving behind a bunch of dust and gas and some type of supernova remnant. But in reality, supernovas can be very situational, fall in several different classes, and in the case of one recent supernova, it's outright mystifying as to just how it could do what it appeared to have. The supernova in question is known as IPTF14HLS. In November of 2014, a survey at the Mount Palomar Observatory detected this object. In January of 2015, it was confirmed to be a supernova, and initially suspected to be a completely normal one that would dim across the next 3 months. It didn't. It continued to sputter in some kind of sustained explosion for over 1,000 days, and searches in past sky surveys showed that this star had previously flared up in this way in 1954 and later. As the 1,000-day flare-up progressed, the supernova varied in brightness by as much as 50%, and instead of cooling down as would be expected after normal supernova types, it maintained a constant temperature of as much as 6,000 degrees Kelvin. So how does an exploding star keep exploding repeatedly like this? That's an unresolved question, and while a number of explanations are on the table, none of them quite fit. Now, this object is not located in the Milky Way. Rather, it's in another galaxy entirely. This galaxy is a dwarf galaxy, with a lot of star formation still going on. And galaxies like that tend to have low metallicity overall, which may factor into an explanation for the object. As an aside, this is how most supernovas are studied, intergalactically, because in and of themselves, supernovas in the Milky Way are moderately rare. But when you have millions of galaxies in which to look for them, they become common overall. The star that sparked all of this off is thought to have been very massive, more than 50 times more so than the Sun. That much mass getting blown off in a supernova produces an expanding debris cloud that eventually will form a nebula, much like the famous Crab Nebula, which is the result of a supernova that was observed in 1054 AD and recorded by Chinese astronomers. In the case of this supernova, however, that adds another layer to the mystery. The supernova is producing a debris disk, but the expansion of it is 6 times slower than a normal supernova. It's as if the explosion and the expansion of the subsequent disk are playing out in slow motion. The star has since quieted down and is forming a remnant nebula, as though the explosion is finally over. But given that this star was exploding over 50 years ago only to explode again, it's anyone's guess if it will flare up again. So what exactly is going on here? Well, there are a number of hypotheses, but none are quite consistent with what was observed. Normally, a supernova of this type would consume much of its hydrogen in the blast, and what would be left over would be a neutron star or a black hole. That process, however, is inconsistent with the observations of IPTF 14 HLS. Plus, there is still a lot of hydrogen observable, which is also inconsistent. One possibility is that of a pulsational pair instability supernova. What happens there is a massive star loses mass until it begins to violently pulse, causing it to shed pulses of material that then collide with the previous pulse material and produce flashes mimicking repeated explosions. The problem with this one is that IPTF 14 HLS produced significantly more energy than what is predicted for this type of event. Other options include fallback accretion, where the material falls back towards a star, or a neutron star companion is interfering with the star by accreting material from it and then expelling it as jets. Another is the effects of extreme stellar wind. None quite fit, however, but there is one explanation on the table that is outright exotic, and if it's the case, it's amongst the most violent events possible in the universe. The idea is that very massive stars can get so hot in the depths of their cores that energy gets converted into matter and antimatter, which then annihilates, throwing the star into extreme instability. The outer layers of the star would get blown off, forming the debris disk, but the star's core would remain intact, and the creation of more antimatter would continue, causing the sputtering effect, until finally the star explodes completely and collapses in on itself to become a black hole. Ultimately, whatever happened at IPTF 14 HLS remains an unknown, but there is another supernova that behaves somewhat similarly. I stress somewhat, that we know a bit more about. It's the Eta Carinae star system and lies at a very distant 7,500 light-years from Earth. This appeared to be a normal night sky star shining at 4th magnitude until it abruptly brightened in 1837 to briefly become one of the brightest stars in the night sky. It then calmed down to below naked eye visibility, only to flare up and brighten again in 1892. Since 1940, it has consistently brightened, and is now back up to magnitude 4.5. This has been termed a supernova impostor, in that what initially appears to be a supernova actually isn't, and the subject star remains intact afterwards. The Eta Carinae system is itself rather bizarre in its own right. There are at least 2 stars in the system. The second component is thought to probably be a normal blue supergiant, but the main star is a peculiar star, and the source of the outbursts. This star is crazy. It is known as a luminous blue variable. These stars are highly unpredictable in their brightness, but they've also been known to change their spectra. It's also doing something rather shocking. This star is emitting an ultraviolet laser beam, and it's the only known star currently doing that. Normally, you'd connect laser light with technology, but not in this case. This appears to be a natural ultraviolet laser being created by the presence of a gas cloud. The whole system is enveloped in a supernova remnant known as the Homunculus Nebula, and the conditions for creating such a coherent signal must be very rare, which is why we don't see natural lasers all over, but not uniquely. A star acting as an infrared laser is also known. I think I'd have used a stronger term than peculiar for this one, and if it's not enough that a giant weird star is blasting a laser beam at us from inside something called the Homunculus Nebula, it's also about to finally explode. The main star in Eta Carinae is expected to go supernova itself in the astronomical near future. It's another one of those Betelgeuse-type stars that could explode tomorrow, or not for another 100,000 years or more. But why it's shedding material and brightening erratically isn't entirely clear. Though when it does finally explode, it won't pose a threat to Earth. But it could become so bright as to be visible in daylight and rival Venus in brightness. What's also interesting is in that these types of bizarre stars sort of stand out in the galaxy. If there are other civilizations in the galaxy studying astronomy, they'd know of these same stars as well and actively study them. The idea that our astronomers are looking at the same stars alien astronomers are looking at seems a little bit spooky, but there is actually a SETI angle in all of this. One of the problems within SETI is that to see a transient radio signal from an alien civilization, you need to know where to look in more ways than just one. First, you have to be looking at the right spot in the sky, but you also need to have the right frequency on the dial. And finally, you need to know when to look. It's very possible that radio signals from alien civilizations happen frequently, and because of those factors, we have simply missed it. But very peculiar stars like Eta Carina provide a kind of signpost. When it goes supernova, the whole galaxy will be looking at the same point in the galaxy. That solves the time and the place problems. That has led to thinking that the best time to look for alien contact signals is during noteworthy astronomical events that can be predicted, such as supernovae, if those can ever indeed be predicted with precision. While everyone's looking at it, in comes a coincident radio signal announcing the presence of an alien civilization. To do it, you wouldn't need this to be in the Eta Carina system during the supernova, merely near enough to send your signal, or if it's directed to Earth, do it from behind or in front of the supernova in the line of sight. As to the dial problem, that's an open question, but there are signpost frequencies, such as the 1420 MHz hydrogen line, and our modern receivers can monitor millions of channels at once, so there is a chance that if our SETI experiments are turned on the next galactic supernova, they might pick up any signals from alien civilizations sent piggybacking on the event. Stars eventually die. It's a fact of the universe that they exhaust their fuel in one way or another and eventually die. Some of them, giant stars, might only live for a few million years before exploding as supernovae. Others, such as fuel-efficient red dwarfs, might live enormously long lives and last as much as trillions of years. Still others, like our own sun, will go through stages in life. First, the sun we see now will change its equilibrium and transform itself billions of years from now into a red giant, and likely swallow up the Earth in the process. And past that, it will become a cooling white dwarf, more of a stellar cinder than a star. But there is a lot of predictability here. We know what classes of star will do what, and what will very likely happen to them in the future through the study of stellar physics. But one thing stars generally don't do is just up and disappear. And even if there was a ready mechanism for that to happen, they shouldn't do it on scales of just a few years, other than perhaps a certain type of rare supernova. More on that in a bit. And there are candidates for stars that apparently have disappeared for no apparent reason at all. The story goes back to a 2016 paper by Beatriz Villarreal and colleagues, link in the description below, where they detail that by studying past sky surveys in detail, things that might appear to be physically impossible, such as the rapid disappearance of a star, might be spotted over time. Using several surveys, they spotted one object that was of particular interest. It may or may not have disappeared right before the eyes of our surveys. Fast forward to now, Villarreal and colleagues have released a new paper, linked below, covering what's happened since 2016 in their work. In regards to the object of interest, it's uncertain what happened there, and further work shows that it may not have disappeared at all. Instead, the object seems to still be there, or an object close to its location, but is now significantly dimmer than what was seen in past sky surveys. If it's a star, it dimmed. Now, the reasonable question to ask here is, could the star simply be a variable star? The universe is full of stars that vary in brightness, and currently the prominent night sky star Betelgeuse in Orion is at an unusual low, prompting some to wonder if it's about to go supernova, though that's very highly unlikely. It'll go sometime soon in geologic timescales, but probably not tomorrow. Another option is a red dwarf that happened to be flaring right when the sky survey that first detected it happened to be looking, and it has since calmed down. Not a bad option at first look, since we know that some red dwarfs, particularly younger ones, can produce ridiculous flares that cause them to brighten briefly, and therein perhaps sterilize some poor exoplanet that might be developing life. But there are problems with that idea. If it was a flare, it was very strong, perhaps stronger than anything thus far recorded, and it doesn't really fit the profile of a variable star either. Could other causes be involved? Is it possible that a distant quasar could be the cause, and the data isn't clearly showing what it is? Only more data and study will tell, but the idea of something changing in a matter not easily explained in the galaxy is of course intriguing, especially over short terms such as in these papers, even though the vast majority of detections of this sort of thing will very likely end up having natural explanations. The paper goes on to detail that since 2016, about 100 additional candidates have been found for inexplicably disappearing stars. And while the explanation is probably something astrophysical, there's a chance it might also be a technosignature from an alien civilization. But it's best not to jump to conclusions there. Also in 2016, the star KIC 8462852 was seen to be dimming in a strange way, and was also undergoing a long-term dimming trend that might eventually make it appear to eventually disappear. While an alien origin for whatever was happening at that star was initially on the table because no one at the time had thought of a good natural explanation, it's since been found that very fine smoke-like dust seems to be the culprit in causing the dimming at the star. Though just what the exact circumstances of this are is still an open question, though a new hypothesis suggests that it may actually be a shredded exomoon. It pays to remember, though, that there are many corners of astronomy that we do not yet completely understand. One example of this that may be relevant to this mystery is the concept of a failed supernova. Essentially, what happens here is that a star of a certain mass and size attempts to explode in a supernova event as it collapses into a new life as a black hole. But it happens such that the explosion doesn't actually happen. Rather, the star essentially contains the explosion and draws it in, thus preventing the supernova and simply producing a black hole directly from a collapsing star. These papers remind me of another oddball instance in the history of astronomy, the mysterious disappearing stellar debris disk. I've covered this on this channel before, but I do so again because it almost seems like one of those mysteries of astronomy that was forgotten and not really ever looked into much again. The star is called TYC 8241-2652, and it, at first glance, appeared completely normal. The star was first observed in infrared in 1983 by NASA's IRAS satellite. It was found to be young and with a debris disk of dust glowing brightly in infrared, as it should. Protoplanetary disks like this around young stars are not unusual by any means. Our own solar system, in fact, once looked much like this while the planets were still forming. Fast forward to 2010. NASA's WISE spacecraft observed the star and all of that material was just gone over just a few years, which was confirmed a few years later with the ground telescope. The protoplanetary disk has just disappeared. It should take geologic timescales to clear a disk like that, yet the star system did it within less than a human lifetime. How did that happen? There are no particularly good explanations for this one. Perhaps something caused the debris disk to fall into the star very rapidly, or some cascade caused all the dust to crush into smaller, undetectable particles. But those aren't very good explanations, and to this day, no one really knows what happened at TYC 8241-2652. I think with the research going on, things are going to get almost real time as we look at the universe. Short-term events seen in the universe like this will only grow the list of mysteries, and who knows, someday a candidate may come along that has no good natural explanation, and we are left with only one option, that what we see is an alien civilization.